For more information on the Toronto Audio Engineering Society, go to torontoaes.org. There you will find notifications on our upcoming events, past events, Masters of Audio, and our member showcase. The Toronto AES is brought to you by Solotech, Gear Audio, Sonotechnique, Bell Media, YSL Pro, Electrosonics Canada, BRTB, Global USS, Adamson, Lawo, avshop.ca, Q5X, and the executive team of the Toronto Audio Engineering Society. All right, I am joined with Richard Hess. Richard is a life member AES. We're going to try to nominate him for a fellowship. So he's contributed a crazy amount to the internet, the world of the Ampex forums, the Studer, the tape you carry with you, and you have shared with you wisdom. Richard Hess, thank you for being here.
Thank you, Anthony. It's always good to chat with you. We do a lot of that on AES committee meetings.
They have been a busy thing. We talk about signal, but we don't talk a lot about noise, right? Signal to noise. And I'm going down this rabbit hole with a whole bunch of colleagues about noise. And I thought of you because you are a leading expert in archiving and medium and tape. And I thought that you might be able to speak a little bit about, what kind of noises, what is noise, Richard? And what are we doing with noise? And what type of noises are we running into?
Well, I guess it's very difficult to separate noise from wanted sound because sometimes part of the wanted sound is purposely generated noise, but that's getting ahead of myself. I'd like to start out with a pure sense of a pristine audio recording. Unfortunately, that audio recording needs to be made in a space. And a lot of my experience is pipe organ recording. And this all on the side, not a professional, well, a little bit professional career, but not my main gig. Pipe organs, choirs, and that has to be done in a large space. And symphony orchestras need to be done in a large space. So you already are fighting noise from the standpoint of, well, in one case, a major New York City subway train running underneath the church that had a really great pipe organ in it. So while some of the low frequency noise was generated by or music was generated by the pipe organ with its 32-foot stops, on the other hand, you had the train stop underneath the church, and the trains coming in and going out would really rumble and ruin takes.
Yeah.
And the only way really to get rid of that was another take. But one of the funny things was I had made a recording there, and we'd gotten rid of all the subway, and it was being reissued by a UK label, and the guy took a noise reduction program to it, very, very hard, and it made the boy choir voices sound just horrible. And he says, but that tape was noisy. I said, no, it was Dolby A. It was not noisy. It was the pipe organ that was noisy.
Right. Well, but pipe organs breathe. Like, they have a bellows, and they have chambers, and they whisper, and they wheeze, and they whine all the time, and that's a different kind of noise. That's like on a clarinet or something that's leaking air. That's an even different kind of noise when it comes to the.
Well,
pipe
this
organ.
was this had 30 horsepower, a 30 horsepower DC motor,
okay,
running the blower.
So you can totally affect the tonal characteristics of a piece of music. Yeah, that's very detrimental.
Right, and even the smart stuff like the spectral denoisers, such as the Cedar patents, which Isotope has licensed, and some other people have used. That stuff's very good, but on really clean two mic stereo in a good room of an excellent performance, it takes away subtleties of the music as well. So, but let's look at the noise that gets introduced. So once we have, let's say we were recording an anechoic chamber with great isolation. We don't want to do that because it doesn't sound good. The musicians can't hear themselves, but just theoretically, a very, very quiet space. So from there, you've got self-noise in the microphone/microphone preamp. If you use a dynamic mic, you're limited by the self-noise of the preamp. And if you're using a condenser microphone, you're limited to the self-noise of the microphone because it has a built-in preamp.
Right.
Microphones tend to be 17, 18 dBA equivalent sound pressure level condenser mics. Really good ones are down around 7 or 8 dBA. So they're pretty inaudible in most rooms, and certainly will be inaudible.
Unwrap those numbers for me, Richard. You're a super smart engineer. So when people look at those numbers from a reference point of a microphone, what does that threshold actually mean? So when you say 117, you're talking about its self noise as a microphone.
No, 17. I'm sorry.
Sorry, I apologize. I misheard that.
17 dBA. It's the equivalent of an acoustic level in the room of 17 dBA, A being the weighting curve.
Okay, so if you had a sound that's 17 dBA recorded through that microphone, it is a known output voltage?
That depends on the sensitivity of sensitivity of the microphone. The point is that if you have a 17 dBA self-noise with a microphone, that's actually below the typical just ambient noise in almost every room.
Right. So microphone outperforms, or the room is noisier than the performance of the microphone itself. So
correct. And then you get down to some microphones that are in the 8 dB sound pressure level, and the actual reference is 0 dB sound pressure level. And I know I was throwing in A weighting because that's how it's usually spec, but that is basically your threshold of hearing.
So because we're able to create microphones that perform better than the room's characteristics, we by nature capture all of that noise as part of this recording because the microphones are better than the recordings. But
don't forget, even though the microphone is measured as quiet as the room, it's still introducing some of its own noise because it may be introducing noises in different frequency bands. Like earlier microphones, you'd have a lot of low frequency shot noise from the semiconductors. I think we've pretty much gotten rid of that, but there's still a hiss that is not common to the room. So it does contribute a small amount of background noise to the recording.
So when you say shot noise, like you're talking early ICs, you're talking early germanium transistors, or just dig into that one noise.
Yeah, that's what it was far more prevalent when solid state microphones were first coming out.
Okay, and what was like? How would you describe that noise? Like, is it just a like a static buildup on a transistor, or is it like what is?
I don't know the physics of what causes it, but it is. It sounds a little bit like low level popcorn.
Okay, interesting. I'll look it up. I'll put it on the list. I got other guests. We'll talk to them. Okay, so go into that.
That's not a big issue today, and with our digital recorders where we don't have full 24-bit resolution because we don't have preamps. The analog sections of the preamps contribute noise, but still we're down with an equivalent input noise of minus 128, 129 decibels. So that's pretty close to the theoretical thermal noise of an input.
Jeez, that was a lot in that. That was a lot in that statement. So the microphone preamps operating they're able to operate with a noise floor of 100 up to 128 dB. So that is the internal thermal operating noise, or is that like the noise of the electronics themselves? Like, what is that range, and how does that noise get clarified?
Well, again, the whole goal of this is to keep it below every other noise. So as you add stages, they all add noise, but if you can keep the noise of the stage, say 6 to 10 decibels lower than the noise coming in, it becomes a non-issue,
right?
As far as the whole overall system goes. So, but the point I was making is the 24 bits is I forget the exact number, but it's 10 or more decibels more capable than the analog preamp section.
Right. I get that, and once it's converted, and that ratio, once it's converted in the digital realm, you don't have any of those tape noises. You don't have any of those medium noises. It's in the pure digital form. But in the past, a lot of the recordings that you're handed, they were recorded with analog as their master. What types of other noises are introduced, just like on the medium side, leaving the digital side out of things?
Right. Well, I wanted to say where we are today and then go back to exactly doing that.
Please.
So the first stage you have is you had electronics that were noisier than what I'm talking about today. And so you would have one of my favorite examples of that is a poorly adjusted Shure M67 mixer. And with that, you can have noise higher than analog tape.
Right, just the self noise of the mixer itself.
Yes, because it was designed to work well with ribbon microphones at a distance. It has huge amounts of gain, and because of that, the way it's structured, I modified the Shure mixers that I was using. I was able to improve their noise performance for my applications back in the 70s. But they would add, and I'm not dissing them. They're great tools for football games and things like that. And they've a lot of broadcasts have come through them. But for high quality noise free recordings, they would certainly not be my 10th choice today. And I mean, Mackie and Yamaha mixers, not being super, they're not Neves, but they're so much more quieter than we had when I first started doing field recordings in the 70s. So but the noises, and you go back even further, you go back to the 40s and 50s, although some of that tube gear was very well designed, it certainly doesn't have the dynamic range of the equipment we have today. So you've got the background stuff. Right. And then you have to put that on a medium. And we can go back to electrical transcriptions, which can actually be quite quiet, but they pick up a whole bunch of surface noise with use. So that isn't a good long-term solution. But when tape was introduced, it actually raised the noise floor of recordings from what people were able to get with electric transcriptions, ETs. We throughout the existence of tape, we were fighting noise and distortion. Right. Although some people like the distortion because it's euphonic.
Sorry, and there's different distortions there. There's harmonic distortion, there's saturation distortion, there's other kind of harmonic noises that get introduced with those tapes.
And intermod, don't forget that. That's not necessarily harmonic. It's the product of two sounds.
Right. So when you say electronic transmit ET, you're talking like a record vinyl. Like a needle cutting into a groove, and that has, like you say, surface noises, and those surface noises are like they're particulate, like in you can't get rid of them, or they change every time you deal with it. And do you do record transfers, or is it mainly tapes, Richard?
It's mainly tapes, but I have adopted a policy over the last decade that if a client has some discs in their collection as well as tapes, I will, if they're within the capability of discs I can transfer, I will transfer them as well.
Right. Well, geez, man, we could do a day topic on your craziness that you do for the world. When people give you tapes, well, or let's talk about tape. When people give you tape, noise comes in the form of surface. It comes in the form of distortion. It comes in the form of mechanical noises, wow, flutters, stretching, et cetera, et cetera. What are some of the things that people give to you? What are some of the noises that are medium based? And what are some things that you recommend to people who are maybe holding on to tapes and holding on to that medium for the next 5 to 10 years? What is some of your advice, Richard?
Well, it may sound self-serving because I'm in the business of digitizing tapes, but I really think that anything you want to keep at this point, you should digitize as soon as you can, because
Absolutely.
we are seeing all sorts of degradations, not necessarily to create audible problems until they create the giant audible problem of the tape oxide on the floor. And that's an absence of sound rather than a distortion. So we're seeing more and more problem tapes that are harder to recover the sound without tape-induced degradation. But I'd like to go back for a minute, if it's okay, and talk about the historic aspects of how we dealt with noise.
Sure.
On tape. The worst noise of tape. Well, there are two sources of noise. One is low-frequency noise, which is generally introduced by DC magnetism on the tape, and that can be easily avoided, although playing the tape on a magnetized machine can introduce that noise. So it's rather annoying, and it can sound sometimes like a burbling as well. So, but the inherent noise in the tape system is the tape hiss. And we have gone through many different techniques. I presented on that at the AES in New York a couple of years ago, I think 2018, on many of the ways, and there's a PowerPoint slide set around that talks about it. But we started out with doing equalization curves that would better match the available dynamic range across the spectrum to typical music. And by typical music, at that point, we were talking about big bands, orchestras, pop music. Not electronic music that would push things far outside what a wind-blown or bowed instrument would produce level-wise and frequency-wise. So that's where we get some of the curves. The typical NAB curve also includes a boost during the recording in the low end so that you could reduce some of the hum that was hard to get out of early recordings.
Right. So like a compensation. So they did they tried to compand the problem by
No, not compand really, because that implies active gain riding, which we'll get into. But this would just equalize it so that the lower frequencies would always be louder, whether they were loud or soft. And that is why a lot of people who do what I did, but before I knew as much as I do now, I was using the NAB curve to record pipe organs and ruined a couple of good recordings or made them less good by having low frequency intermod distortion, which was because of the NAB boost. And the Europeans knew that early on, and the IEC curves do not have any of that boost. That's strictly a North American or US function where it was introduced.
And what happens when the overmodulation happens at that low frequency? You say the noise is like it's not a warble, but you said it was that low frequency intermod. What type of, because it was overcompensated, what does that do to the medium, and what does that do to the playback preamp?
Well, it saturates it, so it does generate some harmonics as well as intermodulations between notes. So it just sounds uglier than it should.
It just sounds ugly. So tube amps are second harmonic. A lot of digital stuff is third harmonic. Is tape different, or does tape depend on other things? Like what type of harmonic?
Well, tape itself is it has, one of the reasons people like it. It does have a lot of, I believe, second harmonic distortion. I honestly haven't gone into analyzing it in that detail. So but I believe that that's one of the things, and it's soft knee rather than hard clipping, are what make it more euphonic for guitarists. Because, for example, because one of the things that happens is tape will start to limit, but gently. And going back into the physics of it, I would say it's because you have particles of different coercivity So some particles would stop following the curve and become nonlinear, but not all of them. So that I think that might be why it's why it's a softer knee. But then Jay McKnight of Magnetic Reference Lab and Neil Bertram, a physicist who worked for Ampex and other things, within the last 5 or 10 years, have said that how bias works is not fully explained by the current literature, and they've been trying, but unfortunately with Neil, his health has not been as good as he would like, and I don't think he's up to finishing the work at this point.
Oh, it's too bad. Like there's a lot of magnetic research that is lost with a lot of these fellas, and to your point, as people, you're got to get your stuff transferred because the machines are dying. The people who know how to make the machines are dying. Nobody's investing in new machines. So yeah, it's very important to get this stuff off as quick as possible.
Well, I'm not making any promises, but I've been wondering how I could best capture my knowledge for a time when I won't be around. And I'm thinking of putting together a handbook.
Hey, that would be fantastic. There are several sought after books in the world, and it's all people who like yourself who have a wealth of experience who find those tips and tricks and put it down. All the world's knowledge, it's in books, Richard. So please, I'll buy the first copy. Right. Definitely, I'll buy the first copy.
So here's the here's the challenge we have with tape, and I feel it's an area that I bridge to some extent. Is there's the scientific approach to all of this, and then there's the craft approach. And people who focus on either end to the exclusion of the other end up missing important things.
Right. But they share a common understanding. So it's a matter of knowing what those parameters do or knowing what those harmonics do and kind of bending things. It's always bending things, right? So the person recording in the past was bending the technology to their needs, and the person today who's using it as a noise distortion tool is bending it in the exact same way, but maybe the opposite.
Perhaps, yes. The thing that I wanted to learn enough about when I was doing a lot of my learning was to learn how far I could go in breaking the rules without causing problems.
So do these things, like you say, breaking the rules, do these things wreck the electronics of tape recorders?
No, it's just the end result. That there were, when I first joined ABC in New York, there was a lot of very rigid thinking about everything was a 600 ohm power match. No, I'm sorry, 150 ohm power matched analog transmission line. And I had already had my nose in recording studio hardware, not actually working in studios, but looking at it and understanding how it went together, and realized that the Europeans and most recording studios had a much more user-friendly approach with voltage distribution, which was why in 1980 I did a convention preprint at the AES convention in New York about what we had done at WABC TV, where the rest of the plant was 150 ohm power matched, and we built the plant as based on the DBU, which is a voltage level reference to a 600 ohm system that is power matched. It's the same voltage as a 600 ohm power match system, but we did some conversions so that things would work well with the 150 ohm power match system, and it was pretty transparent. You could patch across the way we designed things and be able to address both systems, but not have when you're within the island, you didn't have the loading effect. You could mult two things if you needed to without that 6 dB loss.
And that's a lost art of impedance matching, and we have another guest we're gonna talk to about that. I want to still talk to you about medium now. So now, okay, right. so we have all this noise. So
let me go back. So we got sidetracked a bit.
Yeah. Let's talk about noise.
I am, because equalization was driven by noise and distortion. It was to find the sweet spot to maximize without overloading the tape with but keeping the signal as far out of the tape noise floor, which was the dominant noise floor in once it was introduced.
Right.
So we had equalization first, And there's a graph in the MPEX 300 manuals, I think, showing the incompatibilities between the MPEX curve and the Ranger tone curve and a few others. So there was not interchangeability until NARTAB, which was the predecessor of NAB, came up with the standards in the 50s.
Interesting. So it was a trade organization that set that up. So without an alignment of trade organizations like or vendors, it didn't happen. So there was incompatibility like between reels of tape. Like, really? Wow.
Yeah. And with LPs, I don't know the full story. I've never, really understood all of it, but LPs required different curves for playback in the 40s and 50s.
Yeah.
As did 78s.
And the RIA curves and I guess,
Before the RIA curve. That's why the RIA curve happened.
Right.
So that was the Record Industry Association of America, and NAB, or NARTAB, was the National Association of Radio and Television Broadcasters.
CCIR or CIR? What's the CIR?
CCIR is something in French, and that is the European standards, and the CCIR standards are different from the NAB standards.
So now that it's digital, it's all the same frame rate or format or sample rate and bit rate. So we're very lucky we don't have the formula incompatibility of medium.
Right.
Yeah, that's a big deal.
So anyway, moving on from equalization, in the 60s, 3M with Dale Menken and Jack Mullen invented something called Dynatrack, which used 2 tracks of the tape for each audio channel.
Okay.
And they were recorded at different levels with automatic switching between them, so that as you were getting close to clipping the low-level channel, the audio would transition and pick up the high-level channel and drop out the low-level channel.
That's quite the hack. That's an impressive hack. That's a very impressive hack.
And what's interesting is I bought a Zoom F8 a half a dozen years ago when it first came out, and I really chuckled when I saw they have a mode where you set up 2 channels on that for backup recording, so that you can set 2 different record levels, and it doesn't offer automatic switchover, but it gives you the option in post to picking the low level or the high level signal.
Well, and that's a luxury, and they didn't have that when they had tape, unless you had Dynatrack, which they probably made how many machines of it. So
in the low hundreds, I think.
in the low dozens, maybe. Well, that's very interesting. And Dolby and all the different other companies, they've done noise reductions. So yeah, what about those guys?
16. Well, Dynatrack. One of the things that was wrong with Dynatrack was that it used 2 tracks of the tape for one audio channel, and that came out just before multitrack became the thing. So people would much rather have 8 noisier channels than 4 quieter channels for most pop records.
This is true. This is very true. Yeah.
So, and in fact, a lot of people use 24 track, which the track width is the same as on quarter track stereo on 1/4-inch tape. So.
Right.
So the noise performance of the 24 track machines, even when you buy a $70,000 shooter, is still not what it could be with fewer tracks. And a lot of people have said they prefer the sound of 16 track to the sound of 24 track.
We had a 24 track and a 16 track 820 at a studio I worked for, and the 16 is better. It's much better.
Yeah. So and of course, when you have all those tracks, every time you double the number of tracks, if everything is at the same level, the noise goes up 3 decibels.
Right. So there's a physical association with noise too, and there used to be like a lot of thought put into that, right? Like you say, you have a mic pre with this dynamic range, well, that's so the next step has less noise to deal with, and then it's so the next step has less noise to deal with, and it's so the
well, maybe
next
it's
step.
better to say you design the next step so they contribute no additional noise, effectively no additional noise.
No additional effective noise. Richard, it has been a pleasure chatting with you about noise. We got to check in with you more often. I miss, interacting with people because of the COVID and stuff. So it's been fantastic having you part of our subcommittee on standards and interconnection. I look forward to your contribution on the documents and so on and so forth. I'm gonna nominate you for an AES fellow, and I'm gonna try to do that this year. I don't know how it works, but I'm gonna make an effort to make it happen, Richard. So thank you. You be well.
So,
for more information on the Toronto Audio Engineering Society, go to torontoaes.org. There you will find notifications on our upcoming events, past events, Masters of Audio, and our member showcase. The Toronto AES is brought to you by Solotech, Gare Audio, Sonotechnique, Bell Media, YSL Pro, Electrosonics Canada, BRTB, Global USS, Adamson, Lawo, avshop.ca, Q5X, and the executive team of the Toronto Audio Engineering Society. All right, I am joined by Jim Meyer. Jim, are you there?
I am.
All right, Jim. Jim, little bit about yourself. You work for a famous touring company, and you've been with them for a while. Who do you work for?
Clair Global Corporation.
So, how long have you been with Clair Global Corporation?
It's been 33 years.
33 years, and you started, fresh out of school. It was your first job out of school.
It was.
What was the first thing you designed for Clair when you were out of school?
First thing designed. That's a good question, because I was so young. I didn't necessarily design things early on. I was, sort of training. The first real project I had, we had a Harrison SM5 monitor console that was in the back of a truck, whose rear brakes locked up and lit the whole trailer on fire. And so half of the console was burned. And when I was hired, someone else had been halfway through the project of trying to revive this console. All the spare parts were purchased and everything, and I was put on that, and I rebuilt it from scratch.
Wow.
And it saw another 10 years of touring after that.
Trial by fire. So you really did. Yeah, you really did, start at the... And you're the chief engineer at Clair Global, and for the touring section, not for the installation section, for the touring section. Okay, yeah, so you design not some of the equipment, but you design the processes and blocks of Clair Global. What does that entail? Like what does that actually mean?
Well, we treat almost every aspect of a touring sound system as a collection of blocks, right? So you have speakers, and you have speaker cables, and you have amplifier racks, and then you have drive rack and consoles and stage collection systems, microphones. So when I say building blocks, we actually build and test those things as independent things, and any one of those parts might get upgraded over time as an independent entity. We might institute a new amp rack or a new speaker and reuse the other parts. So I'm constantly just keeping in touch with those building blocks that go together to create a portable system. I mean, they literally are building blocks because they're in the truck as their individual pieces, and they show up in the venue at 8 o'clock in the morning and start coming off the truck, and they have to go into their respective locations and be put together and be ready to go by 2 o'clock in the afternoon, and then be torn down again after the show and put back in the truck.
And you've seen every piece of gear, and how we met was through the subcommittee on standards and grounding, and you presented a fantastic paper, and we'll talk a little bit about the paper on microphone splitters. But you said like the building block, usually the first thing to come out of the truck is distro, right? Feeder. Like Clair is known for manufacturing high standards of equipment to tour those high end clients. What are some of the requirements for touring needs, and what is unique about a portable AC system, to control your noise floor, to control the best signal to noise of your sound system? What are some techniques that you've learned through your experience on these building blocks?
Well, the requirements, the first requirement is that everything can come out of the Cadillacs, the road cases, and connect in and be connected correctly. So we obviously pay a lot of attention to what types of connectors we have, where those connectors go, so that our road crew can direct stagehands, because in many places our road crew aren't even allowed to touch our own equipment. They have to direct the stagehands. That connects there, that connects there. So we certainly spend a lot of time in creating organized methods for how everything plugs in. But we pretty much are self-contained in most aspects. So we have all the cabling, all the distro and everything are coming off the truck. So it's exactly the same day to day, and we know how to assemble it and service it. As far as noise goes, you have to pay real attention to cable lengths. The actual topology, star topology is ideal whenever possible. So
and when you say star topology, you mean like you're treating your distro point as a grounding star, or are you treating it as a load? So talk about the star topology there for a second.
Yeah, so I mean, typically the stage left side has the primary distro, and that's considered the star point for the safety grounding as well as the reference grounding for the audio. And it'll typically branch out from there. That'll go to the stage power that's on stage. It'll go to the monitor amp racks that are driving the monitor speakers on stage. It'll go to the monitor console. Those things are all generally right there at stage left. And then it will branch out through a typically 100-meter snake out to front of house. The front of house gets its power from that distro. Most times there is an actual separate distro on its own service on stage right, and that's the only thing that is feeding is the stage right PA system. So that's not so much of a star, although we use transformers to isolate the audio feeds going from stage left to the stage right to avoid any grounding problems across stage.
So when you have
that distro at stage left is considered the star point.
The star point. So before that star point, there's power supply coming into the venues where the lighting will pick up power, and where video will pick up power, monitor walls will pick up power, pyro will pick up all these other utilities. So what do you do to treat those types of signals differently, or what do you do to make sure that you're immune to the noise that those other systems are going to create around you?
Well, the obvious thing is that we don't allow any of the lighting ground, the video ground, or anything to connect to our ground anywhere. We make sure everything stays isolated. So it could be that our primary distro is plugged into a surface that's being shared with lighting or being shared with video, or it could be on a generator. An outdoor show, it might be one generator. And sharing the same service. Now, usually on a generator, in the modern era, there'll be separate transformer services off of that one generator. But even so, even if the lighting service pollutes the shared ground, it doesn't really matter, because we just consider the ground at our distro as the holy ground, even if it happens to be going up and down relative to earth ground or to the video ground. As long as once it gets to our star ground and everything else is referenced from that, then it doesn't matter if that's a little bit dirty.
I've always seen, somebody takes a laptop from video world and they want to plug it into audio world, and it just goes nuts. As a building block, what type of techniques do you have to, eliminate these types of cross contaminations between systems, and what kind of techniques do you employ to make sure that these grounds don't contaminate one another?
Well, that's pretty much transformers. When there has to be audio swapped between say video, video, obviously they're going to play back a video and they're going to give us an audio feed. So we have these small transformer boxes that we've designed that we'll put between our systems so that it isolates those grounds. I've not heard about the laptop cross connection, but I'm sure our road crew, I'm not a touring person, so I don't see everything that actually happens. Our road crew are make it happen out there. They deal with those kinds of things, and if it's dirty, you say, okay, we'll stop doing that.
All it takes is for you to see 120 volts on a HDMI connector one time to change your opinion, just one time.
Oh yeah, you always. We come back with equipment blowing up. It's not. There is a certain connector in the marketplace right now that's very, very common, that if the person connecting it knows how to connect it, they will always connect it correctly. However, it's got 3 tabs on it, one a little bit bigger than the other, and it's possible to rotate it 120 degrees and force the wider plastic tab on the plug into the narrower plastic slot in the outlet.
Yeah.
And so we come back with some of our self-powered subs are particularly prone to this because it uses this connector, and they come back blown up because they got 120 volts on their ground. Yeah,
and it just goes through the audio circuit, or it goes through the audio console even. It depends which one they plugged in first, right?
Yeah, generally for the thing for us is usually it's just one of our self-powered subs that's backwards, so it then goes to the other self-powered subs that are plugged in correctly. So usually it flames something there, and we use Lake LMs, rack mount devices to tie our subs into the rest of the network, and it does tend to blow up the output stages of the lakes. But if those subs were connected directly to the console, it would blow up the console. But our system isn't designed that way.
Right. Yeah, that's what I meant. The speaker processor. Of course, you've got something in front of it. Yeah. So one of the most interesting things that you presented was a document on microphone splitting, and I'm going to share this with the group, and we're going to be able to publish this with your permission. And it was a very kind of counterintuitive document about microphone splitting options, and you broke down a hard split, a transformer split, and an active split, and this all relates back to impedance loading and matching of consoles. Could you tell us a little bit about, at a venue, now that we're still dealing with digital consoles, every talent wants to have control over the gain. Every talent wants to have control over, their tone and their characteristics. What were your goals of this research, and what were you trying to show when you found these microphones connecting to multiple consoles simultaneously throughout your various pieces of equipment that you've had?
Yeah, that document, we service our clients, right? So our clients decide, for the most part, how they want their system set up. There's obviously a traditional is a front of house console and a monitor console. Some artists want 2 monitor consoles and 2 monitor mixers because they want, one mixer on a couple of members of the band, another one on some other members of the band. And each of those mixing engineers wants control of their own preamp. So they generally don't want to share. They may have a brand preference for a certain type of preamp, but really they also want control. They don't want someone else to adjust the preamp gain on a particular channel and them not have that control. So our clients force us to figure out a way to take each of the inputs, all the microphones and DIs and whatever, and figure out how to split those to multiple sets of preamps. And so that's really where this document comes from, is because you can do it a number of ways, but they all have their advantages and they all have their drawbacks. Cost, reliability, independence of control, and even sonic quality. There are some cells there in that table that people are surprised about, like the sonic quality of transformers. That can be an issue. People don't think about, if you have a long cable, the capacitance of that cable on the inductance of the transformer can actually cause some high frequency variations. There are non-obvious things when you use the different splits. And of course, the hard split is the cheapest one, right? Because it's just several wires wired in parallel. And then we have a stage box where we do that split internal to the whole box. It's got, a bunch of XLRs in and several multi-pins out that are all just in parallel with each other. And we have versions of those boxes with transformers in them for the clients that want that. But that's more expensive, and can degrade the sound, the transformer distortion at low frequencies, as well as capacitive loading that I mentioned.
Yeah, you said also that when you do the split, there it's almost like business advantages, like fault protections, like you said, if a cable is shorted on a passive split, everything goes down, right? You had a discovery of pad buttons having an interesting effect on loading. What was that? And could you talk a little bit about that interesting part of things?
Sure. Well, when each console has some sort of input impedance or resistance. We generally just talk about it in terms of the resistance because for the most part it's fairly flat. And all of those, if it's 2 or 3 consoles, sometimes 4, a recording truck might come in one day, those resistances all parallel together to create one loading on the microphone. And dynamic microphones are like loudspeakers. Their output impedance is not flat versus frequency, and it's not 10 ohms either. It can be 200, 400. We've seen dynamic microphones that have an output impedance near 800 ohms. And so if you have all these consoles in parallel, they load down the microphone, and at certain frequencies they load down more than others. And at the frequencies where the microphone's source impedance is higher, you actually get level loss at that frequency due to the loading. And so the sound of the microphone actually changes with the number of consoles put on it. But if any one of those consoles changes their input impedance, that can also change the sound of the microphone. And that's what you're referring to, that sort of a pet peeve of mine, something I always try and I measure on all the consoles that we use, and that there's usually a pad button. In the modern era of digital consoles, it may not actually be a separate button, but it's always there. It may just kick in at a certain range on the knob.
Right. Or it might be a relay. In some microphone preamps, it's a relay that does switch in some kind of H resistor pad or some
Correct.
kind of,
Yeah. And usually on the digital consoles, it's a relay, but some manufacturers actually give you a button on your console that controls that independently of the knob and lets you decide when to kick the pad in or not. And other ones don't give you a separate knob, and they automatically kick it in at a certain range on the knob at maybe 20 dBs from bottom. They turn it off.
Right.
And then you have no pad, and then when you turn it back down to where you don't need as much gain, they'll kick it in. And the design of that pad is the resistances used in that pad can be completely independent of the resistances on the internal preamp itself.
Right.
And so that I've seen, there's one console that was very common where when the pad was off, the input impedance was 10K, and when the pad was on, it was 4K.
Right.
Ohms. And there was I can think of another console where it was about 3K versus 1.5K. So when the user has the button, they're like, oh, that changes it. But the problem is that they're hearing the gain change at a 20 dB gain change at the same time. So they actually have to change it and then adjust by 20 dBs to get back to where they were. And if they do that, they might realize, wait, it doesn't sound the same anymore. Especially true in the modern ones where it's just 1 dB step, right? Where the internal to the digital console, the a 20 dB analog pad is being done, and a 19 dB digital pad is being changed to get that 1 dB step. But the input impedance is step changing on the microphone, and all of a sudden the microphone sounds different tonally, even though you've only changed the gain by 1 dB.
Interesting. So by trying to correct for noise, let's call it distortion, in correcting for distortion, a solution for distortion noise causes a different type of signal degradation that we never think about.
Yeah, it's literally like EQ. You could, if you knew exactly what the output impedance of the microphone was and what their loading on the console was, you could take a parametric EQ and fix what just happened.
Right.
But that's not an obvious thing to do. Nobody knows, I've got to now go add a 1.5 dB boost at 150 hertz to compensate for the fact that the loading on my microphone has changed.
One of the big problems in broadcast is, everybody wants to share the microphone preamp, and here we're talking about mic splitters, so everybody can, make sure that their levels stay the same, their response stays the same with the microphone. What are your thoughts of like the future of the microphone preamps for sharing control? What are touring organizations? What's the trend? Is it Dante? Is it AVB? Is it some kind of proprietary thing? What is the biggest challenge of sharing that gain structure as a system as we go into the networked audio world?
There are several challenges there. The first and most obvious one is if it's one set of preamps, that's one brand of preamps, and front of house and monitor mixers often have preference for a certain brand. They may claim that they like a certain sound of a preamp versus another. So that's one possible challenge. Assuming that they can all agree, okay, we like the brand of this one preamp, so let's make that the single set of preamps. There still needs to be a mechanism where the analog gain ahead of the A to D converter can change to avoid clipping the A to D converter, while not affecting the mix balance of all the consoles that are after it. So there has to be some synchronized mechanism where if the analog gain at the very front end has to change, the digital gain at the back end being distributed over Dante or Milan or Ravenna or A67, whatever you want, that digital gain then has to be trimmed the opposite direction. And
compensated for it, yeah.
So that the mix at each person's doesn't change. Because we're in the middle of a show, right? If that has to change, depending on which direction it changes, you could all of a sudden send the monitor mixer into feedback in the artists in ear monitors, and that would not be a good thing. So so that has to be well controlled and taken care of.
Well, and you're right. It's definitely all about control and venue control, and like you said, the backline, controlling the backline and putting the backline as part of the audio system, because it's not part of the video system. It's part of the audio system. It's and that's something that we're constantly dealing with. So now with the AVBs and the Milans, is there a digital noise that you're starting to deal with now that you're seeing, like, are there new noises in 2021 that we need to look at? What's new and hip in noise in 2021, Jim? What have you seen that's something to look out for, or now that we're dealing with RF microphones, digital mixing consoles, analog splits, what can we expect for noise in 2021?
I think it's fair to say that we are in a better place than we've ever been, right? The fact that now the front of house consoles preamps are on the stage, so their grounding is locally referenced instead of over 100-meter cable. All the things that have happened over the years. And then, being able to convert at the source and transport digitally over Dante or whatever if necessary. Those are all great things. And so we really see a reduction in noise to where our crew doesn't have to spend so much of their day trying to figure out where that hum or buzz is coming from. What I can say, when you say new noises, the more common things, and they're not really common, they tend to be rare and abnormal, but when they happen, they're difficult to track down. Cell tower cows. Or not tower, but cell cows, a local, if you're, and I don't really know that much about it because I'm not into the cell provider world, but I know that it has happened at some of our shows where all of a sudden there's these strange digital noises being picked up in the system, and it turned out to be a cow, which is, I don't remember what it stands for, but or cell on wheels or something like that. So instead of a fixed tower, they literally bring it into an area where they expect a high density of people in their cell phones,
right?
So that they can have increased coverage. But then, that could be a fairly strong RF interference. And so we've definitely had tours that have gone into a specific venue where they spent a lot of time on the given day trying to figure out what the problem was. And in many cases, they have to get somebody to move that, whatever the, whether it's a cow or sometimes it's some other RF transmission device. And they either have to get them to move it or turn it off for the show.
Man, that's fantastic. Jim, thank you for participating in the Audio Engineering Society. You're a fantastic contributor to the SC, the Standards Committee groups. I appreciate your contributions. Thank you for chatting with us today. I know you guys are going to be out on tour for the rest of the summer, right? You guys are vaccinated and on tour. Is that what's happening in the States now?
Let's hope. Yeah, I mean, I am. I got my second dose, and we're doing reasonably well here in the U.S. I'm not so sure worldwide. I I don't think anybody really knows because when touring can start, because I think the CDC actually is the one that is preventing it right now. But when they start issuing guidelines that it can happen, I know that the industry is raring to go.
Yeah. Jim, thank you so very much. I appreciate your time. Ciao, ciao.
You're welcome.
For more information on the Toronto Audio Engineering Society, go to torontoaes.org. There you will find notifications on our upcoming events, past events, Masters of Audio, and our member showcase. The Toronto AES is brought to you by Solotech, Gear Audio, Sonotechnique, Bell Media, YSL Pro, Electrosonics Canada, BRTB, Global USS, Adamson, Lawo, avshop.ca, Q5X, and the executive team of the Toronto Audio Engineering Society. Fran, are you there? Are we synchronized?
I am. I did the clap. We're synchronized.
We got the clap. We're synchronized. Hey, fantastic! Thank you for joining the Toronto Audio Engineering Society for this meeting on noise.
Oh, I'm glad to be here.
Hey, cheers! Wait, what time zone are you in?
I'm Eastern Time Zone, Philadelphia. So
right.
we're time partners. We're pretty much, in the same.
We're vertically aligned. Yeah. I get that. Have you been jabbed?
Same longitude.
Are you? Have you been jabbed with the COVID shot yet, or?
Totally vaxxed. Actually, not only am I fully vaccinated, but I had my annual blood work done last week. My doctor tells me I got excellent antibodies. She complimented me on my COVID antibodies, so I'm 100% immune.
Hey, I enjoy that. That's I'm happy to hear that another a celebrity, cherished designer in the industry is all right. We've had a couple of people in our community who've been affected by it, and it's good to see that you're continuing and you've gone forward with that. I appreciate that. Thank you.
You as well.
Your current time obsession is a YouTube empire. You were a designer. You've collected. You've done guitar pedals. Your pedals they're selling like NFTs in 2021. They're hot commodities. You're a tonesmith. You've created multiple different fuzz tones and you've reissued things. Fran, welcome to the Toronto Audio Engineering Societies.
Thanks for having me.
I am very interested in a conversation we just briefly had about reissuing chips and making chips behave over a period of a couple different dies. Could you tell us a little bit about how Frantome and FranLab became in your world?
Oh wow! We have more than a half an hour, right?
Let's do 15 minutes on this, and then we'll talk about noise. Weave in the noise as much as you can.
That's a long story.
Hey, cheers.
Frantome was sort of just a serendipitous thing. I was working for a guy who I was managing a rental business where I'm sure you have them up there too, where it's just sort of a place where you can rent everything from like party tables and popcorn machines to like, jackhammers. And it's like anything you can think of, trucks and everything, we rented it. But I was managing his business but he had come from an electronics manufacturing background. He was a long-time executive at Digital Equipment Corporation, and so he was there for the golden age of digital through developing hard drives and instant replay, stuff like that. So we talked a lot about electronics and stuff, and I was tinkering on the side just for my own use, and building little things I needed for doing recording and such. And I had tinkered together a little effects pedal on my own just because I needed one. And there was just some day came when we were having the conversation, and he was like, well, I'd really like to get into manufacturing again. And, he said, I don't care what it would be, just kind of a widget. I was like, well, what do you mean a widget? And he said, it doesn't really matter what it is. I just want to make something. When, we were working at this, rental store every day, and at night we would be brainstorming about what could we do. We had some extra space in the shop and everything. And I thought, well, why don't we build a little manufacturing operation here? So it was just kind of, we were just going to try building something. I said, well, I don't know if it'd be a good product, but, I made this thing, and I brought in this little box I built. And I said, well, and he didn't know anything about effects pedals. But I explained, and we talked about it over the course of months, and we decided to do it. But we went down a path where, and I made videos about this, so with the long story. But we ended up making a prototype pedal that I thought was beautiful, but it was unmanufacturable. It was just the cost of making it would have been astronomical, and we really didn't have any means of.
Wait, was it just too complicated inside? Too many parts?
It was a custom cast aluminum case.
Oh wow!
It was custom electronics. Almost everything had to be made. It was flocked, so it was a kind of a fuzzy pink pedal, and I had developed my own flocking process. I had to learn how to flock things. And,
what the flock is flocking?
Flocking is it's still done, but it used to be done a lot in toys and stuff. So if you bought a toy animal, it was made of plastic. Sometimes it'd be furry, and it would have like this kind of furry texture to it. And I actually didn't really know how they did it, but I kind of just had to experiment on how to flock things. And so I developed this process of being able to flock aluminum cases to be able to get the pink fuzzy, texture to the case. And we actually had plans that if we were going to mass produce this pedal, that we had a mass flocking machine, and I'm glad that we didn't do it because the flocking it's basically like tiny little trimmings of cloth. Like if you could imagine like yarn cut to like a millimeter long lengths, and then you just have like a vat full of that. I mean, it's like the only thing I could have imagined is if we would have gone into production and I would have been running a flocking machine all day, I probably would have died of flock lung.
This is like boom polonitis. It's only like 2 or 3 people in the world kind of die of flock lung. Well, that's
it would have been. I would have been the first medical mystery solved. Flock lung. There you go. That we did an autopsy. The inside of the lungs were completely pink.
That's it turns out it was a guitar pedal. So just obsessed with it was a texture again, but it wasn't even a tone texture problem. It was the outside texture.
It's completely superficial. Yeah, death by flocking.
So how many pedals have you designed? What in your repertoire?
I manufactured 20 different, give or take a couple pedals over the years, and I did a couple others for other people. There were a lot of prototypes that I didn't actually make into products, but I guess you could count them too. So maybe 30. But I also, when I was working for Electro-Harmonics, I made a box full of prototypes for EH that they never wanted to build, and I ended up not building them either. But I've still got a box of those pedals that do various things. So
working for EH, is that kind of like do a lot of people show up with a box full of prototypes and become the next pedal designer? What is the process working for a company like that, or trying to get your foot in a door in terms of a manufacturer that works at that level?
Well, I just moved to New York. I didn't have really didn't have any prospects for a job, but I basically just walked in. This was in '97. I just walked into their office, and the manager at the time, it was the hiring manager and plant manager. I just literally walked in, sat down with them, and they knew who I was. They knew my work, and they just hired me on the spot. So there really wasn't a lot of negotiation. It was just the fact that I had been making pedals for a number of years, and that the Frantone line had enough of a reputation that they just hired me on. So that was my CV. But the prototypes, I built them there because a lot of times I was bored. But I had this little shop in my apartment, my tiny little apartment where I could tinker together things. And I was always working on new designs and trying them out and bringing them in and saying, hey, do you want to build this? And they'd try it out and they'd go, it's not really EH or whatever. And so I still do have a pile that I had built.
So you're okay. So you're talking about a noise shape, and you're talking about a character shape, and you're talking about a tone shape. So let's talk about that. Like, what is it in these things, and what is it that gives us this lovely other side of noise that is like a craved thing? What is it about the electronics?
Well, years ago, I was in radio for a long time before I did Frantone, and before I had that job that led me to Frantone. I was actually a professional radio DJ, and what I learned in the radio business was that little trick, sonic trick, was that it was long believed and sort of discovered in the industry that the human ear prefers to hear a little bit of distortion rather than like pure tones. So in the processing, like on radio, making the sound of the record or the CD a little nonlinear, a little distortion, it makes people perk up a little bit. People want to hear it. They prefer hearing a sound that has a little bit of distortion in it, and it's something to do with the way harmonics work. But it's more pleasing than the pure tones. So there's something fundamental about the human audio processing that we have in our brains that makes it desirable to hear distortion, to hear noise. It's sort of akin to, spicy food. It sort of defies logic that we would want to eat chili peppers.
Right.
But we do. There's something in our brain that makes that, desirable. But there's something about noise that also has. So with finding like good tone, it's always riding a very fine line between pleasant distortion and unpleasant distortion. But the certain amount of nonlinearity does make sound more edible to the mind. Let's
back that up. Okay, when you say nonlinearity, so
Right.
let's break down because you can talk about voltage, time, frequency. You can talk about nonlinearity. So when you say nonlinearity, in what way are you manipulating it, and what way is it important in the tone creation that you're after?
There's lots of things that can be defined as nonlinear. If you have a pure sine wave into a device, if you get that exact pure sine wave out, regardless of its amplitude, if it has exactly the same characteristics in the waveform, then by definition you have linearity. So a linear amplifier is going to reproduce that sound without changing the characteristics of the waveform itself. It might amplify it, but the amplified waveform you get out is going to be essentially a exact carbon copy of what it was seeing on the front end. And that's really the definition of linearity. So when things go nonlinear, they can go in lots of different ways. You can have tonal distortion, you can have phase shifting, you can have signal compression where you basically are just kind of squishing the amplitude. All these things are nonlinearity. And to a certain degree, having combinations of these effects really is the essence of audio processing and effects. That's really what we're doing. Mm-hmm. We're manipulating time, phase, tone, and various harmonics and audio compression. But these are the things that sort of come together. We can mix them up in different ways. But all these things are nonlinearities, and each of them have their own sort of pleasing tastes and sort of flavors, if you will.
Mm-hmm. And these are the tricks, the ways that you trick these nonlinear characteristics out of components and signals that are passing through them are very important. So
yeah.
So because they're tricks, none of these things are in data sheets. You're asking components to behave outside of their normal operating conditions. Right. How do you characterize this? How do you make it do the trick you want it to do?
Trial and error. I think that if you're exploiting a facet of a device that's outside of its design characteristics, it's really a matter of just setting it up, punishing it, and seeing what happens. That's sort of what I was doing with the LM386. But other times it's a matter of really trying to operate within the specs or pushing the limits of the specs. Like with the Vibutron, I was using a frequency generator that was really supposed to operate at 18 volts. And I wanted to make it run with a 9-volt pedal, which was really outside of its operational specifications. But I had to come up with ways to filter out the chips that I got to select ones that would work within my specs. So I learned that they had a kind of a wide latitude of operational tolerance in the signal generator, and so that was the 8038 CPD. And so I basically would order a bunch of chips, and I had a bench setup where I would have a sine wave in, and I could measure the distortion and everything, and the amplitude and various waveforms. And I just plugged the chip in, and then I could put it through all kinds of different tests, and I would look for the linearity and make sure that I got the right frequency range and everything out of it. And if it passed, my specs, then that went into a bin that would go into a pedal. And if it didn't, then it would go into a bin, would go into another pedal that I was making that would run at a much higher voltage, and it wouldn't matter about that. So there are also tricks you have to do to kind of work outside of the specs to get a component to operate within the specs that you want, not necessarily what's in the data sheet. Because there is a lot of latitude you'll find in those kind of specifications, especially like operational voltage, output, the kind of output you can get from amplifiers and such, and the kind of frequency ranges that amplifiers will work in. So you can push it, but by being selective, because there's always a certain number of dies when they're making these chips. There's certain tolerances, and so depending on how they're making up the dies, with the process. Some batches are going to work in certain parameters and others won't. So every now and then you get lucky and you'll get a batch of chips that'll work really great at either a lower voltage or a higher frequency or whatever. And you kind of seek out to find lots that are, going to be for just in the right tolerance band for what you need. So it's a combination of finding out what a chip can do, and then if you're pushing the limits, being very selective and just trying to find the freak prints that are, etched outside of the design parameters that the manufacturer is saying it'll do. So it's both sides.
Interesting. So my curiosity then is, like, as a guitar pedal manufacturer, people call you, it's noisy. People call you, I blew it up. People call you, hey, it's kind of, I operated it outside your spec. Hey, I put 18 volts AC into this thing. Yeah. What kind of protectionism? What kind of circuit protection do you have to build into these pedals to buffer the outside, the unknown before you and the unknown after you, to be as low noise as you possibly can? Because these are just amplifiers, like you say, about to take off. Yeah,
it's a very good question, and it's actually pretty tricky. There's two ends of it. There's the audio side, like you said, like audio distortion and stuff, and you want to have the effect work a certain way, but also there's the power side and the interface. So you have interfacing issues because you have to design an effect with the idea that it's going to be working in coordination with other equipment. See, in the early days when I started out, I really didn't know any of the industry standards, which there weren't that many for effects pedals in the 90s. But when I started making effects pedals, I wasn't given any thought to the idea that my pedals would be in chains of other pedals or hooked up to pedal boards and have to interact, with, in a pedal environment. And
systems, yeah.
Right. So the early designs, I didn't have any input buffering or anything on the audio chain, and it sounded great actually, with having really no input buffering at all. Going right into LM386, the early Hepcats, I thought they sounded really crisp, and they sounded great, but early on people were blowing them up, working them in pedal chains where just static discharges and stuff would be taking out the first chip. So I very quickly learned that you have to design an effect to sort of be like an iron box. You have to protect it on all sides. So you have to have input buffering, you have to have output buffering, and you have to have power buffering so that no matter what people plug into it, it won't catch fire. And finding ways to do that would preserve the characteristics that you want was tricky. input and output buffering for the audio is pretty straightforward. You end up having capacitors to buffer the inputs and outputs from DC, because a lot of effects chains have pedals with active switching, especially some of the older ones, and they would have DC offsets on the audio line quite often. And so if you have a true bypass pedal after a pedal that has active, transistorized switching, often you'll have a little bit of a DC offset, and it could be like a fraction of a volt, like 0.7 volts or 0.8 volts or something, or like a diode drop of DC above ground. And when you have an actual physical switching the audio chain, and you've got a little DC offset, you end up with the switch pop. Ooh. And so that ended up being a big problem.
The thumping noise. That's the thumping noise. So the thumping noise you're saying is like a DC leakage, like
DC offset. Yeah, DC, because when the contacts make and break, if you've got a DC offset there, you're pulling current when you break the connection. So and that gives an audible ponk when you flip the switch. So, but that's a very common issue with mixing true bypass and active switching pedals. Not so much nowadays with pedal boards, because pedal board manufacturers are sort of caught up with that. So usually they have like active switching pedals, like isolated with like a true bypass, like their own little circuit and stuff. But in the early days, it was a problem. And with power, there was an evolution. I had an evolution with my input protection on the power. I used to have a passive crowbar, which I did with a Zener diode and like a 10 ohm power resistor. And it basically would just passively sit there without taking any power from the input. But if you put in too much voltage, the Zener would clamp and bring the voltage down. And if you flip the polarity, the Zener would basically act like a short and ground itself and self-destruct like a fuse to protect the circuit inside. But people were blowing up my crowbar, so I was replacing them and stuff. But when I came out with the reissues this time around, I went with an active crowbar using a PTC, or a positive thermal coefficient thermocouple. So with PTC,
so it heats up and cools down, and instead of a fuse.
Exactly. So with the PTC, instead of a resistor, the Zener diode, if you reverse the polarity, the PTC heats up really fast, and it just basically, the resistance, because it's a positive thermal coefficient, as the heat goes up, the resistance goes up. So basically, it just acts like an open and protect. So it's sort of like a very simple, cheap, resettable circuit breaker. But it works, but it protects against reverse polarity. But the advantage of doing that, rather than having the traditional diode in series, like just a power diode in series with the voltage, is that you don't have the voltage drop issue. Because if you want to have like 9 volts of headroom in the effect, like to get maximum performance, and some of my effects like the Vibratron stuff really have to have like 9 solid volts to perform. Shaving off that 0.7 volts or whatever, just having that diode, that's doing some serious, compromise. So having the passive crowbar in there, it was a way of getting around losses, so I could maintain my 9 volts, but still have protection.
So maintaining the signal to noise ratio, or the distortion potential ratio, I'm going to call it the distortion potential ratio in this case, is important to your design. So your pedal can perform to its maximum in its range.
Well, yeah, because some of the designs, I ended up with the reissue of the Peach Fuzz, I ended up taking out the 386 third stage and replaced it with a rail-to-rail op amp. So with the rail-to-rail op amps, it will output to the VCC. So whatever your supply voltage is, it's not like you have a diode drop or a volt and a half below supply. You can actually get peak all the way up to top. So the difference in like a volt makes a difference in the performance, 10% or more. Yeah, totally. Difference in performance. So, so it makes a difference. Like I said, in things like the Vibratron, where I was already running, the chip out of spec, running 9 volts, running, 8.2 volts. It's like, no, then you're really pushing. So yeah, there were lots of reasons to have like the not only 9 volts like at the jack, but to have 9 volts like at the circuit.
At the circuit. You said something that struck very clear to this conversation about noise, and that's the fact that, like you said, it was an iron box, the shielding enclosure, the complete encasement of the amplifier. Why do you do that in your designs, and what are some things that people do wrong, and what's the secret behind that iron box and that shielding enclosure?
Well, the primary reason for the full metal enclosure is just isolation from radio noise, RF noise, and stuff. I learned that was another mistake when I made my original prototype for that effects pedal that we started Frantome with. I put it in a plastic box. I actually demoed it like a few months ago. I did a video where I pulled it out and fired it up. It still played great, but it was like really noisy and hummy and stuff because it's in a plastic box. So there's absolutely no isolation from all of the radio noise, ambient noise from switching supplies and just the buzzing and clicking of everything that makes RF noise. So putting the enclosure, using an all like aluminum enclosure, you basically have a Faraday cage around the circuit. So as long as you have good grounding on the audio and power, then you've pretty much protected your electronics from external noise. But that doesn't mean that you don't have to deal with internal noise sources. That's a totally different issue. But it eliminates the external by having it in the enclosure.
So you say, what you seeing? Are you seeing a lot of equipment now that are made out of these plastic boxes, or is there something inside these plastic boxes, like a shield inside that they're doing?
No, I mean I think aluminum is sort of the standard. Everyone's using some form of die-cast aluminum box these days. Even the tiny ones are all metal. So I mean, there were some. I think Dane Electro and some had some plastic boxes. I imagine they'd have to have some kind of foil, inside or whatever. But if you go with plastic, because it's cheap, then you have to have that sort of cage around the electronics. But I think it's just bad design to have a plastic enclosure. Not the least of which is that it's breakable.
You're gonna get stepped on a million times. Like,
yeah, I used to in the early days, because when I started using the die cast, it was kind of unusual because in the 90s when I thought of effects pedals, I was thinking of the EH pedals and stuff. They're all in those sort of folded metal
sheet
designs,
metal, yeah.
Sheet metal that you could drive it over with a car and just flatten it like a can. So I originally we were thinking that, well, it would be a great demonstration to get like a video camera, and because we were the guy that I was working for, he had a plane. So I had this idea that I would take a Hepcat and I would demonstrate it on the ground on video. And then we would go up in the plane and we'd fly around, like get up to like 1,500 feet over a field. And I'd drop the Hepcat out the window, for a 1,500 foot drop into a field. We'd land in the field. I'd walk up to dig up the Hepcat out of the ground or whatever, plug it in and play it.
It's rude not to. You got to do these things, and your guitar, like you've done a lot of guitar videos. You play in a band, you record stuff. Guitars are these magical things that always go into pedals, and one of the things is every guitar I've ever dealt with is a great antenna, and you're always feeding it into, like you say, amplifiers that are, borderline exploding. Why do guitars behave the way they do? And what are some things tried and tested? Maybe Franz, we'll wrap up here with maybe like a tips and tricks for guitar players who have that buzz, hum, and rattle in their instruments.
Yeah, well, but you said it. The guitar is a perfect antenna. I mean, it's you got a coil of wire in there. And you're taking that coil of wire and you're running it through another really long wire and putting it into an amplifier. So, single coil pickups are notoriously hummy. That's why the humbucker was invented, using two coils and using phasing and such to try and cancel out the very common noise that you get from the 60 or 50 hertz hum of the electrical equipment that comes from light fixtures and the amplifier itself and everything. That it's a common problem, and anybody who gets into music, if you're really not experienced in grounding and dealing with noise, if you get out and tour, the first thing you're going to encounter is that there's going to come a time when if you're playing a single coil pickup guitar, when you're going to get up on a stage and you plug it in and it's just humming and there's nothing, and you just can't find the thing. But there are lots of tricks. You start to learn about routing wires and such, like when you're running your patch cables and things, not to run a lot of cables in parallel. You don't want to be running your audio cables in parallel with power cables on the way to amplifiers and stuff. You try and crisscross, or cross paths of wires and stuff to avoid, inductance and things. And with pedals, because of the inherent problem with radio noise and picking up radio noise, it's very common in pedals to put an RF buffer, like an RF clamp, right in the beginning, so that anything above a certain frequency, like anything over 30K or 40K, is just cut off. You have a flattened off curve, so that it just any radio noise will be eliminated. But the problem is, at 60 hertz or 50 hertz, you really can't eliminate those frequencies without affecting tone. So that it gets tricky. So the RF noise you can definitely cut out of the effect, but the power line noise it's always an issue. But that's why their whole industry is built around equipment racks that will deal with hum or phase cancellation. Introducing a 60 hertz hum that's out of phase, and you can adjust the phase so you can basically cancel out the hum rather than eliminating it from the front. You can actually introduce a 60 hertz hum and just kind of dial in a phase cancellation and adjust the amplitude and take it out. But yeah, there's lots of tricks, but it's always a problem. Noise.
So what's next for FranLab? Can you tell people about the website, how to get in touch, how to check out the channel, how to become a fan and like and subscribe?
Well, it's if you just go to their YouTubes and type FranLab as one word, it'll come up. But it's always something. I've got tons and tons of stuff in there, boxes and boxes of things. I got stuff on the bench right now. I've got some new unobtainium, some stuff people sent in. I've got to fire up. So it's that's the one thing about your channel. Yeah, it's like really rare one-off electronics. I found it's sort of my collection is becoming more and more very rare and obscure things, and people send stuff in that I hadn't heard of. So as many things as I find myself, other people, find things and send it in. And
have you got something on the bench? Can you show us one thing before we take off here?
Well, the bench is way over there.
Oh, it's way over there? Okay. Never mind then.
I'm wired up here.
You're wired up. Okay.
So,
all right.
Yeah, this is the other side of the lab. This is all the store. This is the storage part of the lab. You can probably see behind me various storage boxes and such. But yeah, it'll come up. I don't like to reveal what's on the bench until it's ready.
I get that.
But it'll come around. Yeah, definitely.
All right, Fran, thank you so very much for your time.
Thank you.
We'll have you back again sometime. It was a fantastic chat. Thank you for all your information.
Yeah, I'm looking forward to coming back to Toronto.
Hey, yeah. We'll see you soon.
See ya.
For more information on the Toronto Audio Engineering Society, go to torontoaes.org. There you will find notifications on our upcoming events, past events, Masters of Audio, and our member showcase. The Toronto AES is brought to you by Solotech, Gear Audio, Sonotechnique, Bell Media, YSL Pro, Electrosonics Canada, BRTB, Global USS, Adamson, Lawo, avshop.ca, Q5X, and the executive team of the Toronto Audio Engineering Society. All right, I am joined from Seattle, Washington with Rick Chin. Hello, Rick, are you there?
Hi there, Anthony.
Rick, you are a very Googleable engineer with a long line of credits. You have influenced the audio industry from your early work at a small company called Tapco. You were R&D at Tapco, and what year were you there?
Let's see, 1975.
75, and you were a designer of what sort of product?
Well, I mean, they were fundamentally a mixer company.
Mixing consoles.
They had peripheral stuff that went with mixing consoles. Their dream, I guess you could say, was that everything in the equipment rack said Tapco on it.
Right.
And they tried hard to do that, but they stumbled several times in the process, and that led to them getting acquired by Electro Voice.
And with that, you experienced a career that dived into various fields of technical writing. Your heart was in the electronics of things. You spent time with Fluke Manufacturing. You spent time in the U.S. Air Force. You spent time with other systems. Would you say that you have worked up a career? You've done so much for audio and been such an influence in career. Are you a fellow of the AES? Are you a fellow of the AES, Rick? Can I nominate you for a fellowship? Okay, so all right. So I got to work. This is the second guest that I've had on the show that I've got to nominate for an AES fellowship. I
am just a life member.
You're just a life member. I consider you a famous designer who's influenced every audio company, that has come down to it. And so it's a privilege to have you here to talk about noise. And one of the things that I'm always super curious about is, what is noise? Like in a mixing console, and what is noise in those things in the rack? What is the noise that is injected into these boxes that we create, and why do we have noise in audio equipment? Like, why is there noise? It's such a broad topic, but what is noise, and why do we have it, Rick?
Well, we have all kinds of noise, but I guess in the context of your question, the first one is thermal noise, which is by the minor complication that we don't live at absolute zero. If we lived at absolute zero, there'd be no thermal noise. Now, I've known a few lead singers that I'd like to have live at absolute zero.
The thermal noise is it's like just the action of putting electrons through components introduces noise. Is that?
That's close. I mean, it's the fact that that Brownian motion ceases at absolute zero, and it begins once you leave absolute zero, and it increases the farther away you get from absolute zero. So we're roughly 300 degrees away from absolute zero. So there you have it. And then on top of the thermal noise, which is hiss, then there's man-made noise sources that exist because we figured out how to make electrons and electricity work for us.
Right. Okay. So there's hiss and man-made.
Yeah. On top of the hiss, then there's hum, which arises from magnetic fields, and then there's buzz, which comes from things either working in your near environment that are governed by switching, turning electricity on and off quickly. So that would be things like light dimmers, fluorescent lights, microwave ovens.
Okay, so those buzzes are introduced noise, or are they?
Yeah, they're conducted, I guess, or broadcast. They transmit either electrostatically or magnetically.
I love the word broadcast, that the buzz is broadcast. So okay, so I love this. We've got hiss, we've got man-made, we've got hum, and we've got buzz. I love these. I love these. So then we have physical noise. So let's go to the mixing console. In a mixing console, we have switches, we have potentiometers, we have faders. Why are those things inherently noisy, as they age, and what happens inside those components to create noise?
Okay, well, to start with, other than the fact that in the case of potentiometers and faders, that they're resistors, so they have thermal noise according to their value, the switches and things are just on and off devices. And if they make noise, it's from the external circuit around them. And the same thing with potentiometers, other than the thermal noise that arises from the resistance. If a pot is scritchy when you turn it, it's because it's interrupting some signal.
So it's jumping?
Well, no, I guess you could say that if we put a DC voltage across the pot, and then we rotate the pot, and the wiper jumps on and off of the carbon track, and as it jumps off the track, the output voltage is going to go to 0. And when it reaches the track again, it's going to be at whatever fraction of the input voltage the wiper's at, right? And so right there, you've got a noise signal.
Right. So, and the noise is an interruption, but it appears to be a screech. But what it's actually doing is it's a series of shutting off.
Yeah, it's a variable voltage square wave.
So the noise isn't actually induced; it's actually just a series of things shutting off. Interesting.
Yeah, the output of the pot is noisy because of what the wiper's doing.
So
but
I have this.
The strange thing about that, though, is that if there's no DC there, then the pot is quiet.
So and that introduces, that's why designers they DC block, they put DC filtering, yes. they DC block everything from.
They put capacitors up the yin yang.
So why do we
That's
put
the cheap way to do it?
That is the cheap way to do it. Yes, and there are better ways, but yeah, of course, it's the most cost-effective way to do it. You can't do it at scale, especially on some of the consoles like that you've designed. Some of the scale of the consoles that you've designed.
Although, I mean, it's been done. The company Crest, they were very proud of their consoles having, for the most part, 2 coupling capacitors between the microphone input and the last line output.
Right. Yeah, it is a badge of honor, and I think if you design those things, it's it increases the life of the components as well.
Yeah, I suppose it also directly affects the cost, and because of the extra circuit complexity, you can argue reliability.
Does DC burn audio circuits? Is DC like the biggest enemy of the audio mixing console designer for audio?
No, I think in most cases it's the user.
Well, hey, Mackie was amazing. Like you say, they trained the user before they even bought the thing with their documentation. Mm-hmm. So I absolutely love that. So you said pots, one of the things is a fader doesn't actually turn something up. What does that mean when I say that, Rick? Faders are resistors, you said. So how do they work in the circuit, and why do faders get scratchy? Like, other than the mechanical side of things, like, is it and what have some companies done to prevent this, and what have they done traditionally to work around these types of noise circuits?
Well, probably in the old days, everything was transformer coupled. So before and after the transformer, there was no DC. So inherently, at least from that standpoint, you never had a noisy pot. However, you could have pots that were noisy with signal for the same reasons. You just wouldn't hear them until there was signal. Like if you put a pure tone in it and you turn the knob, and you would hear the audio coming and going as you rotate the control.
Right.
So now we've eliminated transformers just about everywhere, and in most cases we're using op amps and running with bipolar supplies. So inherently the output is 0 volts, but there's always a tiny bit of offset there. And a careful designer can help minimize that offset. And if you really want to go after it, you can add another op amp running as a servo to null out the offset. That's what Crest did. So if you can get rid of that offset, then you have no DC running through your control, and the control won't scritch when you turn it. Now, if the control gets flaky, in other words, the wiper is hopping on and off of the resistance element, then with audio there, as you turn it, you'll hear it scritch. And that's just a clue to you as to what's wrong.
Most of the time, scratchy pots, they're from a, like you say, build up DC burning something, some schmutz, do you recommend cleaning? Like what is the, you're known for your tactical stuff, and I'll talk about your website, Unita Audio Systems. You're a tactical, technical writer of, do you have a favorite potentiometer cleaner, Rick, or suggestions for dealing with those scratchy physical elements of a mixing console?
Well, sometimes you can affect things by cleaning, and sometimes you can make things totally worse. So I guess my favorite cleaner is Kremlin.
Yeah.
Which was sold by Kague Laboratories years ago, and now it's I think it's called Kremlin Inc. And I don't know what it is. It's some magic juice.
That's always the magic juice. It's just it's gasoline that's flavored like raspberries.
Yeah, I don't know. Maybe it's Agent Orange's second cousin.
Well, so hiss.
Anyway,
that's a great one. I like that one. That's good. Yeah,
you could if you can get at the inside of the pot, and you can apply the tiniest drop of the stuff to the wiper fingers, and then exercise the snot out of the pot. Use that motion to spread the cleaner around on the carbon track. Okay, that can help. But if you do what most people do, which is to shove the nozzle from the aerosol can of cleaner and thoroughly douche the inside of the pot, then you really run the risk of screwing up the works.
And everything else, yeah.
You'll get cleaner on the carbon track, but worse is that the Japanese-made pots, or the Asian pots that have that really nice silky feel when you turn them, they get that way because the actuating shaft and the mounting bushing are precision machined. And there's just enough space to let them put in a film of silicone lube, and that's what makes it feel that makes a 2-bit pot feel like a $25 pot.
Yeah,
and it was always something that we wanted to do at Tapco, and we didn't have the money to buy the Asian pots, because even though by the time you were all done they were cheaper, you had to buy a couple thousand of them.
Yes. Yeah.
So that was money that we just didn't have. So we came up with a scheme to make the pots, to make a 25-cent CTS pot feel like a $2.50 CTS pot. That's another story. So, but way back then, if you douche the inside of the pot with cleaner, then the carrier or the solvent that carries the cleaner out of the aerosol can also happens to be the solvent for the lube. And so now when you've douched the inside of the pot, it dissolves the lube and spreads that all over the carbon track. And now you've just made things worse.
So, so consoles are consumables, and really what it comes down to is these things have a shelf life, and they are consumable products, but as a mechanical designer, Rick, no audio designer hasn't been a mechanical designer in their lifetime. we have enclosures that cover these things, and we have ways to protect the noise and the gunk from getting inside these components. Talk about the shielding enclosure and actually, well, let's talk about like what the box of a mixing console is and why it's such an important part of a mixing console system and what it does.
I mean, it's a Faraday cage, so it's stopping electrostatic fields from interacting with the guts of the mixer. And if the enclosure happens to be a magnetic material, then it's also a magnetic shield, which, especially if you have transformers, can be a first level of defense against hum.
So you said like a ferrous metal, a magnetic metal. So it's okay. So if it's a steel box versus an aluminum box, okay, and then you got your plastic mixing consoles.
We did that.
What are the plastic mixing consoles doing in lieu of this Faraday cage?
They're praying.
So what do you mean by they're praying?
They're praying to God that there won't be a magnetic field to intersect the wiring inside the mixer.
So okay, let me unwrap that. So if I have that's a okay. So if I have a
pardon my cheek.
No. Okay, it's a good one because it's an important kind of concept that's deep. So if I have a mixing console, let's just say it's made out of plastic or it has no Faraday cage around it. So this Faraday cage, does it have to reference something in a good design, or what does it have to be bonded to in a good design versus?
Yeah, I suppose it does need. It can't just float in the air. So it needs to go to 0 volts audio.
So some reference. Okay. So yeah. that magnetic Faraday cage of the mixing console is there to protect from buzz, but it is reference to 0 volts audio, your system audio.
So let's have a story here.
Please.
Okay. At TAPCO, we had one of the owners was an industrial designer, and was always looking for a way to make an enclosure for the mixers that was that had more design elements to it than just folded up sheet metal, which is all they'd been in the past, right? So his concept was to make the mixer case out of structural foam, and that would have had some advantages in that since it was molded, we could have more visual elements to the physical design. It could be a different shape, and it would be lighter, so it wouldn't cost as much to ship. So we went out and we blew $1.50 to 2 buckets of money on having a tool made. And of course, this was before Asian tool makers became prominent, so it had to be made in this country. And I'm guessing they spent 10 grand on the tool. And then the first articles came off, and yeah, they looked really nice, and they would probably do the job. And then so we built some mixers, and then it suddenly occurred to somebody that these things were hum and buzz magnets. And the reason was that the case provided no shielding. So they suddenly had to go out and find some kind of material they could spray on the inside of the case that would become that conductive barrier between the outside world and the guts. And in the end, it worked. And those were that series of mixers became known as the wedge mixers because they were kind of vaguely wedge shaped.
I'll look it up. I'll see if I can get a picture on when I present.
If you can, I probably can.
For me, you say buzz magnets and hum magnets, and like what inside a mixing console and a microphone preamp just makes it like an antenna. Well, it's not an antenna. It's an amplifier.
Well, it is.
Okay, so tell me about the antenna that is inside a mixing console or inside a microphone preamp in general.
Well, it's more than just inside the preamp. It's what's connected to it, namely the microphone cable. So there's your antenna. So and the fact that there's wiring inside the mixer to get the mic preamp to the XLR connector, well, you have a short antenna there. But usually there's no problem until you actually plug a mic cable in.
There's usually no problem until you plug a microphone cable in.
Yeah, because you're connecting the antenna to the radio.
So, and that antenna is, if it doesn't have a microphone on it, it's not terminated. But if it has,
even worse.
Okay, so that's even worse. Okay, so what happens when you what does this antenna pick up, and what is it conducting, and what are these broadcasted signals that it's picking up?
I mean, it's susceptible to everything that's in the atmosphere around it. So on a concert stage, then we're talking about junk coming in from the lighting system. If there's radio transmitters nearby, then it's those. If the production company or the event coordinators are using two-way radios, then you've got that. Nowadays we have cell phones. That's something we didn't have 50 years ago. If there's arc spotlights, then that's a possibility.
Bluetooth. You said man-made noises. We have motors around us. We have LED. So in 2021, are there new forms of noise in 2021?
I don't know. Maybe 5G.
The 5G. There is the 5G. Yeah. Well, we can't go into that on this side. This isn't that kind of show.
And that's going to be everywhere.
It will be everywhere. It is everywhere already.
And I think, I don't know what kind of power they run. I think that your average cell transmitter is at least 100 watts.
I'm not, it's been such a long time since I studied it, but I do know that, like you say, everybody's got a cell phone, and everybody's got two cell phones on them, and these are new noises.
Right. And this, cell phones run, their power is dynamic depending on how far away they are from the tower.
Yes.
And the phones and the towers are smart enough to tell the phone what power level it needs to transmit at, rather than always running wide open all the time.
Yes, and the antennas are directional, so they have multiple in, multiple outs that point and can be phase aligned. Anyway, I digress.
It's a wonder it works.
It's a phenomenon that it works, but the telco is, sympathetic to the audio industry and vice versa, right? We all have those same kind of problems. I
don't know how sympathetic they are to us.
Well, I've one of the guests on this show, and I'm going to talk about is an RF technician, and they just moved a whole bunch of frequencies for everybody, and it just made a whole bunch of noise in the industry, and it's a different kind of noise. So, Rick, I digress. You have a website that I consider to be a famous website because it's such a Rick, on your website, you have a lot of audio tactics, a lot of tips and tricks. Tell us about your website and how your website came about.
Well, the website came about, I guess, from I was on CompuServe. They were kind of an early adopter and provider of space for people to discuss whatever they wanted to discuss. And there were a couple of what they call forums, which would be comparable to a Facebook group these days. And I got onto a couple of the forums and was answering questions from people there. They would just kind of post a wide open question, and I'd rein it in and then provide an answer. And I found myself doing the same thing a lot, and so the website was kind of a defensive mechanism where I could write that answer once and post it on my website, and then just point people to it. So it became sort of like an encyclopedia.
And that's the coolest thing about it. Like it is your own private encyclopedia of and they're very quick tips. How did you become such a quick writer, Rick?
Well, that's a good question because, going through school, if you had told me that later in life I would actually do writing for a living, I would have laughed at you and told you were 20 brands of crazy. And going through school never prepared me for thinking that I could write. And it wasn't until, I guess I was busy evading the draft in the 60s and took a remedial English class. And one of the assignments was to just to write something, anything, it didn't matter, and turn it in once a week. And that's what I did. And I think the thing I latched onto was writing about music and musical groups, and found I enjoyed doing that. And then I figured out later that I could write if it was a topic that I understood and knew. But if you ask me to give you 100 words about an onion, you'd get 0. Well, I mean, I guess I could say, well, they stink. When you cut them, they'll make you cry. And that's about the extent of my knowledge about onions.
Yes, but the audio onion, you know very well, and you've peeled it back on a couple of things here in a very simple, easy to digest way. Your pad, like I said earlier, you have a Switchcraft tube pad that I've built probably 50, maybe 60 times in my career. Mm-hmm. Tell us about that. Like, why did you create these tutorials for people, and what was the need for you? Like, was it just notes you had?
Years ago, when I first started doing audio, mixers had fixed gain input stages, and they were made for somebody mumbling a foot away from a dynamic mic. And the thing that made rock and roll sound work was close miking. Get the source up close to the mic. Well, generally when you did that overloaded the mixer. And so the way to fix that was to put a pad between the microphone and the mixer. So I learned how to make pads from the Audio Encyclopedia. This would have been back in 1967 or so. And then there it was a process of finding the topology you wanted to use, and then looking up the factors in a table, and then doing some simple math to turn that into resistor values. But
okay. Let's talk about that pad thing. So what would be the noise associated with not using a pad in those cases?
Gross distortion.
So the microphone in those cases was too hot. And that gross distortion, what is that gross distortion caused by, and what is that distortion?
It's the input stage clipping.
Okay. So what happens when an input stage clips? So if a potentiometer stops, signal, an input stage is clipping. What does clipping an input stage actually do?
It sounds like this.
Okay, so I'm hearing a different preamp from you. I don't think I'm actually hearing that microphone feed fed to me.
Well, I think you do. I turn the gain trim wide open, and I'm talking close to the mic, and my interface says it's clipping.
So I might be. We gave it a shot, and the noise of the thing didn't go away. But if the preamp is clipping, let's take it up from there, Rick.
Then it's fuzz voice.
It's fuzz voice. So what happens in fuzz voice at an op amp level? There is a stage of a microphone preamp or a preamp that is fed voltage. What happens to that voltage to overmodulate and create fuzz voice? What is fuzz voice?
Well, it's a square wave basically, and it's caused by the input signal being amplified enough to go beyond the power supply rails of the amplifier. So
it's starved.
No, it's not. Well, I don't think I'd call it starved. It's overgenerous. It's I don't know. How about taking a drink of water from a hose, but you can't swallow the water fast enough to keep it from leaking.
Okay.
And so what happens? You get wet, right?
Okay.
That's from the excess water. So from taking a drink standpoint, that's clipping.
So that excess water, what is
so
that?
So go back to electronics. Let's say we have a microphone signal that's a tenth of a volt. And I'm going to stay out of dB for now. And we're going to apply a gain of 100 to it. So that tenth of a volt becomes a volt. Let's see, that's 10. And then 100 would take it to 10 volts, right?
Okay.
Okay. No. Yeah, tenth of a volt, 10 volts, yes. And so if the amplifier can deliver a 10 volt signal, then everything's fine. But what if the amplifier can only deliver 5 volts?
Right.
Then we have clipping. And that's exactly what happens.
So it's run out of, well, it's
out of power supply.
It's out of power supply. So when you get into these big consoles and mixing consoles, we're sitting right beside a Neve console there. You were tapping on before we chatted. Why do these big consoles have big, huge power supply rails? And what separates a mixing console from a mixer in the preamp stage? And why are some preamps thousands of dollars?
We have to work backward a ways and a few years. Okay, so in the early days, let's say back to Woodstock time, okay, mixers had fixed gain inputs. So the output of the microphone went into a preamp stage with fixed gain, and then it went into the level control, the mix pot, okay? And you repeated that n number of times, and then you had an amplifier after the mix pots to make up for the loss in mixing, and then a master gain control, and that was the mixer, right?
Mm-hmm.
So we're talking about things like Altec 1567s or Bogan MXMs, or getting a little more recent Shure M67s.
Right.
Okay? But all of those mixers, what they had in common was fixed gain input. So somebody had to make a decision of how much input signal that mixer could handle before it started distorting. And generally, those things were made for speech inputs, like a microphone in an auditorium, a foot away from the talker who's mumbling.
Yeah.
And not made for Mick Jagger, a quarter of an inch from the microphone diaphragm, yelling at the top of his lungs.
Thus the pads.
Big difference.
Yeah.
So the solution, because we had nothing else, was a bag of pads. So we could control the input signal to the mixer before the mixer got it. And so if we could knock that strong input signal down into a range that the mixer could handle without distorting, then we were home free. Okay?
Love it.
So now we'll move ahead a few years, and not that many years, and somebody finally got the bright idea that the input, that the microphone preamp in the mixer needed to have adjustable gain to accommodate the wide variety of input signals. And Tapco took that to the bank with a series of ads because the musicians thought the microphone was overloading and not the mixer. And the theme of the ad was, I don't remember the name of the person they coined to blame this on, but let's call him Mickey. So it's not your microphone, Mickey, it's your mixer. And the Tapco mixers at that time had variable gain input stages. And that was their secret to working in a rock and roll environment.
That's very awesome, Rick. That's thank you for sharing that. That's such a to have been a part of that is spectacular. So we're very privileged to have you here on the show. I still want to pick your brain about noise.
Yeah.
for days. Man-made noise. We are surrounded by computers, and people are taking that, vintage Tapco and that vintage Yamaha PM 2000 and that old McCurdy mixing console and that old Ward Beck, and they're putting them in their studios now, and they're extracting the gold nuggets of mixing consoles that once existed. What are some of the dangers of, you told me about a modification you're doing to a mixing console. What are some of the dangers and warnings you have for the engineers of 2021 when they're doing these types of man-made modifications in these Faraday cages you've built in the past?
I don't know. There's so much different stuff out there. It's I think you need to be able to understand what's going on and what was done before and why it was done before. And these days, I see a lot of people out there trying to do this stuff that I consider hackers.
Right.
And that's using the negative sense of the word that the news media coined.
Okay, and they're by doing things wrong or by breaking the they're not traditions, they're best practices that the AES
they don't really know what they're doing, and so they're constantly on the lookout for recipes, and they have no way to separate the good recipes from the bad ones.
This is true.
How do we know if the recipe came from Julia Child or from Ronald McDonald?
Hey, man, I love Ronald McDonald. That place is efficient. And Julia Child, man, if Julia Child and Ronald McDonald, got together and I could get French cuisine in a drive-thru, I would be amazed.
Around 2001 or 2002, I made my first trip to Europe. And I started out in the UK, and then I took the train down to Portsmouth and took the ferry across the English Channel to, I don't remember the name of the city again. But by the time I was supposed to take the express ferry across, and there was a lot of weather, and instead of taking an hour and a half, it took more like 4 or 5 hours. And so I finally got to France and had to pee really badly. And the first thing I saw that would be open, that would have a usable restroom, was a McDonald's. And I ducked in there and made my business. And then my first meal on French soil was a McDonald's burger.
That's amazing. I do the same. For me, it's like comfort, and the microphones that we have and the equipment that we have are comforting for people. And I don't want to say Tapco and Mackie were anything along those analogies that you just used, but they are ubiquitous. They are absolutely everywhere. Rick, thank you for your time. Thank you for your contribution to audio. I will nominate you for fellowship. So I'll get somebody else to. So that's number 2. So my goal today is to get 2 fellowships. Thank you for your time, Rick.
Okay.
Bye-bye. For more information on the Toronto Audio Engineering Society, go to torontoaes.org. There you will find notifications on our upcoming events, past events, Masters of Audio, and our member showcase. The Toronto AES is brought to you by Solotech, Gear Audio, Sonotechnique, Bell Media, YSL Pro, Electrosonics Canada, BRTB, Global USS, Adamson, Lawo, avshop.ca, Q5X, and the executive team of the Toronto Audio Engineering Society. All right. I am joined on the line by Mr. Bill Whitlock. Bill, are you there?
Yes, I'm here.
Bill, how are you? How's the weather?
Warm. It is
Warm?
a warm day in Ventura today.
Are you vaccinated? Did you get vaccinated, or are you?
Yeah,
Good.
I got both my Pfizer shots in February, actually.
Oh man, well, we're happy to have you. Some of our colleagues in the SC group, one of our good friends, Ray Rayborn, he succumbed to the conditions of COVID, and happy that you're vaccinated. Get out there, be safe, Bill. Be safe.
Thank you. Yeah, I plan to be. Now that I'm of an advanced age.
You joined the AES in the 60s?
66.
66, and you strike me as the kind of kid that was a tinkerer, AV club.
Oh yeah. I was taking radios apart before I was going to first grade.
Taking radios apart. When you were in the first grade, were the teachers always getting you to do stuff? Were you fixing projectors? Were you running around with carts?
That started about fourth grade.
Fourth grade.
Fifth, yeah. Actually, I was repairing things in grade school and all through school. I became the repair tech for all the AV gear. So, yeah, I was good at it at an early age.
From there, did you go to school? Did you do? You were a technician. Did you what did you study? What was your first kind of employment? Right out of school.
Well, actually, in high school, I worked in a TV shop for a big department store in St. Petersburg, Webb City, in a 10-man TV shop, and they all thought that I'd only be good for cleaning out chassis or something when I hired in because I was only 15, and by the time I left there, I was the top tech in the shop, repairing all the tough color TVs and showed them how they could make money repairing old transistor radios and all sorts of stuff. So They were good years. That saw the transition from vacuum tubes to transistors, by the way. So that was how I saw that.
You have worked some top secret missions. You were part of the H-bomb project?
Yes, I worked for General Electric back in the early to mid 60s and had to get a top secret clearance to work there. And it took me almost a year to figure out what they were shipping out the back door were the trigger mechanisms for H-bombs, basically neutron generators, modified X-ray tubes. I think that's why GE got the contract.
And you had a fascinating position that you say really helped defined some of Bill Whitlock, and it was a turning point when you worked at GE. What was your task, and what did you have to deliver?
I worked in, pardon me while I adjust this silly camera. I had a job in what they called this seems to be fighting me.
Oh no,
they called it the components lab, and we basically torture tested and made sure parts were in spec and that vendors weren't somehow seeding the lots, putting good parts among bad ones. So we torture tested resistors, capacitors, semiconductors, diodes. Remember testing diodes for reverse recovery time, which takes some very elaborate gear.
Yeah.
Gains of power transistors at 55 degrees below zero to be sure that transistorized inverter would start when it was really cold. I actually created a breakdown test for mica capacitors because they had identified a failure mechanism where little air bubbles would get into the coating for these mica capacitors, the brown dipped ones. And it would cause corona discharge under high voltage pulse conditions, which would eventually break down the mica and make the capacitor fail. So I developed a test fixture that applied a huge high voltage pulse and then looked at the current circulating in the tank circuit. And you could see the corona as a little fuzz on the waveform.
Wow.
So
that's incredible.
It was fun.
With that, you had access to like military grade precision measurement and testing equipment. What was that like, and how important was that in shaping your future curiosities?
Well, it showed me what's possible, and I love that part because we had nothing but the best Tektronix and HP, and we even had a vibration table where we could shake stuff apart. And of course, environmental chambers where we could create heavy humidity and extreme temperatures. But most of all, it gave me an idea of how individual parts work, and most of all, how they fail. And when I do circuit design, I can't help but think of failure modes. And is this the best dielectric to use in this application, and things like that. It just, I think I was very lucky to have a broad experience base when I was in my earliest jobs in telemetry, component testing. They were some odd jobs, and this is something we didn't even mention before. They were all carefully calculated to keep me out of the military, because the Vietnam War was going on, and that was the last place I wanted to be. So these military connected jobs were sufficient to keep my draft board in a military deferred status.
But you did go on a ship for a while, right? You did.
Yeah, that was as close to the military as I got. I was a civilian employee, but I worked on a 520-foot ship that had 3 huge antenna dishes on the top. It was intentionally sunk off of Key West. It's now a diving attraction. But it used to be my home and my job working. RCA sent me to school at Cape Canaveral to learn inertial navigation and celestial navigation. So I can tell you all about deflections of gravity due to mountain ranges underwater.
Well,
it's crazy.
It is great, but it all adds up, right? It all adds up to be the career that you have. Somebody told me you had a friend who knew the Beach Boys, and that led you to the audio industry, back into the audio industry.
Yes, I went to college with a fellow named Steve Desper, who ended up being the mixing engineer for the Beach Boys for quite a number of years, from that had to be from before 1970 until maybe 1980. So I got to know the Beach Boys pretty well. I used to hang out at their studio. They had a home studio in Beverly Hills. And that got my foot in the door in audio, and that was indirectly my connection to Quad 8, because Quad 8 was the supplier for all the equipment the Beach Boys used and took on tour. So, and that led me to, when I went to Quad 8, I met Dean Jensen for the first time, and that came full circle 20 some years later. And there was a series of lucky connections, but it's where I'd always wanted to be. My wildest dream was to get involved in the music industry. And lo and behold, one thing led to another.
You were an early creator of computer automation consoles. I've seen some of your patents. You've got a couple things. This is you had an interest in automated recording stuff, and you had one of your Quad 8 consoles do a very interesting thing for one of Canada's Neil Young. Neil Young and you did a cool gig with one of your consoles. What did Neil Young do with a Quad 8?
Well, basically a Quad 8. There were a lot of rumblings in the early 70s about automation, mixdown automation. And there were a number of different systems around. Allison Devices had one. There was, and there were various techniques to encode this data and store it on the actual music tape itself, because there were no such things as floppy disks or anything back then. So anyway, I designed one of these at Quad 8, and it was called CompuMix, and it was an add-on. It was a controller that you'd sit down on your console, and a audio pathway for 24 tracks. And Neil Young was one of the early buyers of this system, and he realized, it was either him or his mixing engineer, Elliot Mazer, realized that now they could take a first generation recording, and once the mix was right and had been memorized by the automation, they could play this original tape back and output 2 channels and go directly to disk. They didn't need a master tape. So I was up there working with Neil the day, several days, that he worked on an album called Time Fades Away, which was recorded on tour. And they literally got the mix all trimmed up with CompuMix, and then drove his recording truck over to the lacquer channel in Sausalito and put a couple of cables through the front door and started the lathe and cut that whole album directly from the masters.
Sounds like they were trying to reduce noise, Bill, and I think that's what we're talking about today.
Yeah, there was a lot of clarity. I mean, every generation of analog tape, you lose a little bit, so it was good.
You pioneered some cassette technology when you went to Capitol Records after some time there. Again, in a pursuit of lowering noise floor, you were involved in a lot of technology there. How did your career take a shape when you were a manager of Capitol Records, like R&D, again back into the R&D department?
Well, the first thing I had to do was learn the whole process of high-speed duplication, which took a little while, and I learned more about magnetic tape than I ever wanted to know, but it is fascinating stuff. So we redesigned the entire signal path for a process that Capitol called XDR, for extended dynamic range cassettes. That was their goal. And when we got there, we improved the bandwidth, we improved the headroom, we redesigned the electronics. We actually implemented and designed our own version of Dolby's HX Pro, which actually they licensed from B&O. Headroom extension extends the MOL of tape at high frequencies. So they were amazing sounding cassettes. And then to further improve on that, we came up with an idea for a digital loop bin. And we weren't the only ones that thought of the idea, but we had a unique way to do it.
Sorry, before we go talk about a loop bin, let's back up. So you high speed cassettes. So the high speed cassettes would be recorded at how many times real time? This is
Capitol did it at 64 times speed.
64 times speed.
So the 20 to 20 kilohertz audio spectrum moved up to 1.28 kilohertz, the equivalent of 20 hertz, to 1.28 megahertz at 20 kilohertz. So this, as you might expect, changes the electronics substantially, but you still have to maintain the dynamic range and the low distortion and whatnot, even though you've taken the bandwidth way up. And the bias frequency goes up to 10 megahertz, and the heads are made totally of ferrite and very low inductance, etc. It's a fascinating process. So the XDR cassettes became what I believe is the best in the industry. We had QC that would actually test high-speed duplicated cassettes, and they routinely came out of production plus or minus 2 dB from 30 hertz to 18 kilohertz.
Wow.
Pretty amazing for a cassette.
Well, and it's you're pushing the limitations of the technology to control the noise, right? You're getting dynamic range, you're getting frequency response, you're getting everything to control.
Well, it didn't do much for the noise floor. That's pretty much a constant. That's just because of the narrow tracks and the slow speed of cassettes. It's kind of unavoidable. But if you use noise reduction, Dolby B or Dolby C, I think Dolby B was the standard back then. You could do pretty good. You could get, close to 70 dB of dynamic range, which is pretty good for a cassette. Not as good as a CD, of course, but
no. Well, and your goal was to improve the tape bin. So the tape bin was a loop that fed these high-speed duplicators, and then something later on would cut up these little tapes into different spools. And so the loop bin was noisy, and it was a fail point, right? It was
the dominant failure point in the production line. It was basically an endless loop. You couldn't put it on a reel. So the tape was literally just stands on its edge under between a glass top and a metal two surfaces, and it just folds up on itself as this mass of tape is moving across the table, and it's being pulled out of one side and pushed back in on the other as it's played. And they use air streams to keep it from getting tangled as it gets pulled in. But still, sometimes several times a day, the tape would form a little kink or a crease or something, and you'd hear this like an explosion as this 480 inch per second tape loop came to a halt, and the production line goes down. And because they'd be recording this loop that repeats itself on slave machines, 30 or 40 of them around the room, and they would start with 3,600 foot rolls of cassette width tape, and the girls would circulate around the room, and when one would get completely recorded, they'd put a fresh one on and start it. So you could make 10,000 copies a day easily in that room.
Holy.
and then the loaders were something else to behold. But I don't want to drag this story out too long.
No, well, for me, it's a history, Bill. I love hearing the stories of where we've come from in terms of recording technologies, and but from your time at Capitol, you were designing a project, and the project got mothballed, and you found yourself looking for a new employee.
Yeah, they unceremoniously canceled the digital loop bin because we decided to replace this tape loop with a giant array of dynamic RAMs. And then my design partner and I, another really good analog designer, figured out how to take two 10-bit video speed D to A converters and map them into a single 14-bit ultra high speed DAC to deal with this digital data that we were going to throw at it at high speed.
Wow.
And among other things. And the project was running behind, and the price of DRAMs had temporarily risen because PCs were starting to consume all the DRAMs the industry could make. But the management at Capitol was very short-sighted and decided that they were just going to cancel the project. But what really got under my skin was that they sent me on a vacation and didn't tell me. And when I got back from my vacation, the project had been pulled. Room was empty, all the gear was gone. So I decided to leave.
Well, they binned the project, right? The bin project got binned, so
got bin, dustbin for that. Yeah.
Dustbin for that. From Capitol Records, you found yourselves at working along with a colleague of yours. Dean you'd worked with him. You said at Quad 8, and
he actually interviewed me at Quad 8 to replace him in 1971. He was leaving Quad 8 to start Jensen Transformers. And he interviewed me and put his stamp of approval on to take his place at Quad 8 back in 1971. And we met again after my gig at Capitol Records. And then we started consulting together, doing special projects. And then, unfortunately, about 2 years after we started working together, he was having troubles that I didn't know about at Jensen, and committed suicide and left me Jensen Transformers. So I tackled that. Took several years and a lot of money to dig our way out, and the Isomax product was what saved Jensen. So I was there from 1989 until 2014, when I sold Jensen to our single largest customer, Radial Engineering, again, back to Canada.
Back to Canada. What is it with us and noise and audio? I don't get it.
Must be something in the water in Canada.
Or the ground. Maybe there's a problem with the ground up here.
Ooh, there you go. Oh, ground. Good one.
Well, the Isomax and Jensen, your reputation, the name speaks for itself, and definitely you wanted to preserve that name and preserve the reputation of the company. And like you say, the Isomax entered the home stereo market, the car audio market, some of the studio market. Like, why did people need the Isomax, and why did Transformers solve these noise problems, and what were the problems that everybody was having, and that this one thing that you shot that you created what did it do?
Well, the connection is something called ground loops, and they are probably the single most prevalent source of system audio noise. I mean, anybody that's worked in audio is familiar with hums and buzzes in a sound system, and they are created in the power line. And I've done hundreds of seminars to trade shows and universities talking about where those come from, how they actually get into the signal path. It's the coupling, and that's where common mode rejection comes in, common impedance coupling and unbalanced interfaces, and common mode rejection and balanced interfaces. And transformers, I knew were outstanding at solving all these problems, but I did not understand why. If somebody had asked me in 1990 or 1991 or two to explain why a transformer is able to kill these noises better than anything else, I couldn't have told you. But I made it my business to find out why, and did a lot of research into balanced interfaces. found out how many myths are involved that people actually believe, and started writing about it. And that was my inspiration to write my first paper in 1994, Balance Lines in Audio, Fact, Fiction, and Transformers. And it turned into quite a widely read piece. In fact, AES told Neil and I that issue of the AES Journal was the largest selling issue they ever printed, that special issue on grounding. So
another half Canadian Neil. I guess Neil is an American, right? I think he was born in the States and he moved to Canada. But Neil Muncy, you're talking about there when you talk about Neil.
Yeah,
so
Neil was a great friend and a great colleague. We had endless discussions, it seemed.
Yeah, and you said that he was one of the guys that pushed you to
speak.
To speak.
I was terrified to speak in public until 1994, and Neil knew that I was doing this research on balanced interfaces, and there was an AES meeting in Los Angeles, and he was speaking, and he practically literally pushed me out on stage saying, "You've got to tell these people what you know about balanced interfaces." And I got up on stage and started stammering around, and 15 minutes later I'd lost my fear, and now I do it without really thinking about it.
At the drop of a hat. And this is exactly why I called you. I'm like, who can I talk to about noise that could just spout out for a couple of hours about facts? Well, I'm just
get me started.
I'm just gonna call Bill. This is the easy one. So Bill, I've been on this quest for what is noise, and of course you've done your diligence in this topic, and where does it come from? And we'll talk not about room noise. We'll not talk about maybe some environmental, but a lot of our AES members, they deal with microphones. They deal with computers now that they're at home. They've got multiple computers plugged in going on. They're connecting all these things to audio mixers. People are finding a lot of time on Kijiji and Craigslist, and they're buying old mixing consoles and plugging them in their bedrooms, and of course there's going to be noise in these systems, and you brought it back to power, and you brought it back to ground loops as a system idea, and noise kind of it's not just one thing, it's this system idea. Could you talk a little bit about how these things interrelate, and why it's such a complex topic when Anthony sends you an email and says, "Bill, what is noise?" in 30 seconds?
Yeah, that was a rather nebulous question. Well, let me pose a hypothetical.
Okay.
If we had audio systems where every piece of equipment was powered by its own battery, we could make our systems as large as we wanted, and we would likely never hear a hum or a buzz. Because this stuff comes from the fact that equipment is, by and large, powered from the AC power line.
Right.
And there are properties of the power line that I won't go into here, but I've written papers about for those that want to dig. There's an AES paper called Ground Loops, The Rest of the Story, published in 2011. And it explains exactly what goes on inside the walls of your building that create small voltages between that third prong on AC outlets. If you were to put a sensitive voltmeter between any two of those in a room, you will find a small voltage, and it will be almost exactly what you normally hear as bzzzt.
Okay, whoa. Look, let me unwrap it. Okay, so if I have two plugs in one room, between the safety ground, or are you talking the neutral?
Safety ground. Safety ground.
Between the safety ground, there will be a difference there, and that difference will be directly proportional to the buzz in your signal.
Well, that's where the buzz originates, and it's created by magnetic fields in the premises wiring, where the neutral and the hot wire and the safety ground all share the same space. As currents flow in the line of neutral conductors, they create magnetic fields. And if the safety ground conductor gets a little closer to one of those than the other, it magnetically has a voltage induced over its length. And that's and the reason it has to do with its proximity is that theoretically, the instantaneous current in the neutral and the line, or the hot conductor, are exactly the same, but in opposite directions. Therefore, the magnetic fields that they create in those two conductors are opposing. And if we could get those two conductors to be in the same space, those magnetic fields would cancel and disappear. Well, the only conductor arrangement where there's a complete cancellation is coaxial cable. And I doubt that we're going to see 120 volts AC wired in buildings in coax.
Yeah. We finally just got rid of the knob and tube. We just got rid of the knob and tube. So, it's not, somebody comes along, hey, what you really need is coax. It's like, no, we're going to
get laughed out of town.
We're going to shut that down real quick.
Right.
So a lot of these systems are out of people's control. Right? Like, and I don't mean to interrupt your butt. I hope it continues here. No. A lot of these systems are out of people's control. So a lot of people, they, is there a way that people, there's a proper way to build these rooms, and there's a proper procedure to build these rooms, and not all of these rooms are equally the same. And do people make assumptions, or do they just take these things for granted when they start building sound systems and recording studios in these places?
I have a very well-known client right now that I can't disclose their name, that I am advising the electrical contractor as they are building a very large building where they intend to put a lot of instrumentation. I'm telling the electricians how to do the detail of their job. And of course, they don't like it because it's extra work. But electricians wire a building so that lights work and toasters work, and they don't give a second thought to noise in the building or how it's created. So an electrician wires a building, and he'll walk away when the lights work and everything you plug in works and fuses don't blow and nobody gets electrocuted. But for noise, like I just mentioned, the magnetic fields in the conduits is critical because that's the source. And the best thing you can do if you're wiring a building from scratch is to take the line and the neutral, the white and the black wires in North America, and twist them, just like we would twist the conductors in a mic cable to make it immune to magnetic fields. The magnetic field around current-carrying conductors is a two-way street. If you twist a conductor, not only do you make it less susceptible to magnetic fields being turned into signal voltage in the pair, but if there's current flowing in the pair, like there is in AC wiring, you make it less able to create an external magnetic field around that pair of wires because you're putting them very close together along their entire length. So those fields tend to cancel unless you get extremely close to them, where you can actually get closer to one than the other. And this technique can reduce these ground voltage differences by a factor of over 1,000. That's 60 dB of noise reduction. But electricians will look at you like you're from another planet when you ask them to do this.
Well, at least you're not asking for coaxial 125.
No, but the looks are just as weird. Let me tell you.
So I've seen this stuff. So they get a big drill at one end and they stretch out 100 or like a whole spool. And are they twisting spools, or do you rent them a piece of equipment that spools white and green wires together?
Well, I don't actually do this work myself. But,
obviously,
I did some testing for the purposes of the paper. But the first building that I'm aware of where this was done was a colleague, a guy named Jamie Fox, who I first met at Cal Poly up in San Luis Obispo. He was a student member of the AES up there. And he was a major in electrical engineering, and he went to work for an electrical contractor that got the job to do the wiring at the Bing Auditorium at Stanford University. And he convinced them to do the twisting for all the wiring in the sound system. And they found a wire supplier that pre-twisted these pairs and put them on giant reels and were delivered to the site.
Cool. So
all they had to do was pull them in just like they would normally pull untwisted pairs into the conduit. But there's a set of rules. You need to use insulated or isolated ground outlets so the grounds don't get tied together through the conduit and they're mounting. And you'd need to do this twisting. And those are the two basic techniques that can reduce noise system-wide by some 60 dB.
That's incredible. That's unless you have the mind of Bill Whitlock and the money of the Bing Auditorium to accomplish such an experiment. I'm glad it was done. Thank you. I don't know if, I'm glad somebody, did the experiment and has the test report to prove that. That's phenomenal, actually.
Well, and the people that installed the sound equipment were amazed.
Yeah.
Because they put the entire system together and there wasn't a single bit of noise encountered anywhere.
That's, it's diligence. I think it's diligence to system design. But
you have to understand the physics. I mean, that's what it all boils down to. Faraday's law. It works.
So a lot of people, they have their home studios and they're not running everything off batteries. They have DC plugs absolutely everywhere, and you have audio equipment that is made out of plastic now, and you've got synthesizers that are like I say, made out of plastic, or they're we're into modular synthesizers where there isn't even a Faraday cage around some of these devices and apparatus. The manufacturing has changed, from the days of Quad 8 building, solid metal consoles to 2021. What are some of the things that we've taken for granted in previous, construction techniques that have completely been disregarded in some of the new modern designs that are wreaking havoc in the world of noise?
Well, I'm not sure anything has really been disregarded. We've had hum and buzz problems back when I worked at Quad 8. That was very common. The solutions were a lot more crude and very often didn't work very well. I've seen massive copper bus bars put into recording studios, basically trying to take all these little voltages that are created in the ground system of AC power and trying to short them out by the time they get to the console, where there's some mecca, of solid copper for all the grounds, and patch bays can turn into nightmares.
Yes.
But if most of these systems are in buildings with conventional AC wiring, so it's just a fact of life that these voltages are there. The best you can do in a sound system is, because these noisy ground voltages are the result of the length of these ground connections in the conduit, just plugging everything in your system into a single outlet strip where the ground connections are very close to each other in the strip is a huge help. And in fact, power conditioners, like $3,000 boxes with a row of outlets on the back, most of the effectiveness of those boxes at reducing noise comes from the fact that they're basically an outlet strip on the back. Right. That's what's doing the noise reduction.
That it forces the user to plug everything into it, thinking that they have some type of magical protection. But in reality, what they're doing is they're bringing the ground and the bonds closer to one point, which gives them the...
Right, and to each other, more importantly.
Yes.
All the system's grounds, if they could terminate in a point very close, would solve the problem. So in a lot of these boxes, your $3,000 power conditioner is basically a $3,000 outlet strip.
Right.
The rest of the stuff in the box is sometimes superfluous and sometimes literally superfluous.
Well, and that's a hard part about the hi-fi audio industry and the home audio industry, and that I'm sure you've had some tinfoil hat wearing guys at your booth at Jensen when you're at the home theater shows, and we have them all the time at the AES members, and we welcome everybody with tinfoil hats at the AES events as well. So I imagine you've had some unique noises, some truly unique scenarios, but the most common people come and they want to solve noise problems. Is it always come down to, I can sell you something, but it's probably something else, or I could show you this ISO solution, or I could teach you the ways, but it's likely not the thing that's going to solve your problem? Do you find yourself in that, or have you found yourself in that scenario quite often?
Statistically, 90 to 95% of noise issues, hum and buzz, are due to these inter-outlet ground voltages. And if you can't change them, if you can't rip open the walls and start twisting and putting in isolated ground outlets, which gets pretty expensive unless you're doing new construction where it's relatively cheap.
Yeah, and if you've gone that far, you might as well twist your ground and neutral, right, folks? Like, if you're gone that way, this is it from now on. I'm definitely twisting them, that's for sure.
Well, it turns out you don't want to twist the ground wire with the other two. You want to twist all the current carrying conductors together.
So
not the ground.
So neutral and
Neutral
hot.
and it's corresponding, or if it's a three-phase circuit, you take all three of the phases and the neutral and twist them together, because collectively the net current is zero if you get them all close together. But you want to leave the ground wire out of the twist.
So
it's a nuance difference, but it's significant.
I love it.
Because there's in the U.S. there's type MC, which is an armored hospital grade, or well, I don't think it's hospital, but it's often used in hospitals. But it's where all three conductors are twisted together.
Okay.
And its performance isn't quite as good as twisting just black and white and leaving the green out.
But you also have the shielding of the. So what does the BX or the conduit or the armor or that do to the system and versus something that is not something that is not I did something there.
Non-metallic.
Yeah, a non-metallic thing. What happens that
we did that in the AES paper, in the 2011 paper. We used what's it called, EMC, basically ferrous tubing.
Okay.
EMT, that's what it's electromechanical tubing, versus PVC. And the difference is very small. The metal apparently increases the coupling at very low frequencies, kind of predictably by a few dB, but then it has the opposite effect once you get above a few kilohertz. And one of the important points about this stuff that goes on in the conduit is that because this is magnetic coupling and the induced voltage in the ground conductor is proportional to the rate of change of current, translated, that basically means it couples much more voltage at high frequencies than it does at low frequencies. And that explains why things like phase control light dimmers are such a problem.
Oh, yes.
Because when they switch on and off, they do so very, very rapidly. And that rapidly changing magnetic field can induce tens of volts over a 20-foot length of ground wire in the conduit.
And let's that is the biggest one that I've heard, and it's always lights. Like, it always comes down to lighting, and
lighting people again.
Well, so and the new lights are cheaper. Lights are new in 2021. Like, they're not the same light bulbs you had in 70s when you did quad 8s, right? Like, it's a totally new light bulb. What are those LED lights doing to our environment? And like you said, pollution of grounds. But like, I look at a light and it doesn't have a ground, Bill. It doesn't have a safety ground. So how is it polluting my system, and how is it polluting the environment that I'm trying to make this capturing this performance happen?
Well, I think there are probably, actually, I don't have much direct experience with LED lighting, but it operates at higher switching frequencies. Most of them are digitally controlled. And if they meet certain specs, because the FCC also has specs, and well, for that matter, so does IEC, about conducted interference on the power line. So it could be that they are a lot more friendly to systems than conventional light bulbs and old phase controlled dimmers. Those are gradually fading away, but there's still a lot of them around.
Yeah. Yeah, and when you say phase control dimmer, so there are a couple different kinds of dimmers. There's like a rheostat. There's like a big resistor, and then there's
the the variable transformers. Those are really big, but they're very quiet because they don't
expensive.
do any switching.
Very expensive
and bulky.
And bulky, yeah. So then I have to ask. Okay, so there's buzz, right? And that's your
right.
That's that. And hum is kind of in the buzz category. Is hum in the buzz category?
It's a spectrum difference. Hum is like pure 60 cycle AC, the fundamental frequency. Now, if you turn that into pulses, buzz is basically like listening to the power line, but turning the bass all the way down and the treble all the way up. Right. Because that's what happens in this coupling in the conduit. Is that it's the induced voltage? If you hold the current constant, the induced voltage will rise at 6 dB per octave with frequency. So by the time you get up into approaching 100 kilohertz, which is the conventional phase dimmer that we just talked about, the kind you buy for $10 at Home Depot.
Yeah.
Those, because of their switching speed, create very strong harmonics up to at least 60 or 70 kilohertz. So they induce very large voltages into the ground system, really big, tens of volts easily. And that, then works its way into the signal paths through, imperfect rejection in balanced interfaces and directly in the case of unbalanced. And that creates a lot of noise because you can't hit an audio front end with a spike that's 10 times the size of the signal, even though it's at an ultrasonic frequency or a very narrow pulse, without creating a buzz.
That's I love that. And then you said hiss is a different kind. Hiss is a different noise.
Yes.
And
hiss, if you read books on noise, every conductor has molecules and atoms in it. And of course, electricity is the movement of the atoms of the electrons from one of the atom to atom. So random noise or white noise is sometimes called the eternal hiss, and it will be made by even a piece of wire at room temperature, and it's sometimes referred to as thermal agitation noise. The only way to make that noise go away is to take the conductor down to absolute 0 degrees.
Right.
Minus whatever 270 something centigrade, where electron motion stops. But so white noise is directly proportional to temperature, and it's even made by a resistor. And the higher the value of the resistor, the more voltage noise it makes, and it's also proportional to temperature. A hot resistor makes more noise than a cold one, but it's something that we're stuck with. And there's similar kinds of noises in semiconductors and vacuum tubes. So any noise that's truly random in nature is probably a fundamental noise that will never, ever go away. That's why there'll always be a hiss in the noise floor of a microphone preamp, because the gain is high enough that we can actually hear that thermal agitation noise in the copper wire that the microphone coil is made from, or a resistor that might be in the circuit. And some people actually waste money on very exotic resistor material, as long as I'm on this subject.
Don't go.
A little pet peeve of mine, to buy an expensive metal film resistor where there is no DC voltage present. Because all resistors make the same amount of noise sitting by themselves. But then there's something called excess noise, where if you put DC through a resistor, like you would in circuitry for bias or collector load resistors or whatever, now there's additional noise made, and this is called excess noise. And this is highly dependent on what the resistive material is. Carbon resistors will make 100 times the noise of a metal film or a wire wound resistor. But when there's no DC present, all resistors make the same noise. Carbon resistor is the same as a wire wound, as long as there's no DC.
So in audio circuits, we're constantly fighting DC in audio circuits, and designers are constantly fighting DC in audio circuits.
I don't necessarily mean DC offsets in the signal voltage input or output. I'm talking in internal circuitry.
Okay.
Where a power supply current is flowing into a transistor collector or something. There you have to be very careful the kind of resistor you choose.
You've talked a lot about interconnecting audio equipment, and you've talked a lot about power systems, and then on top, the one thing I find is you can do all of this. That's great. That's fine. That's fantastic. And then you get some vendor, some manufacturer that has a power supply that is generating noise or is noisy in some way, shape, or form. What is it about power supplies and the ways that they do things that can be transmitters of noise, opposed to being some things like they may clean up the circuit they're in, but the thing themselves is a transmitter of noise. What are power supplies doing to our noise floor?
Old brute force power supplies rarely did that because they operate at 60 cycles. The old power transformer, rectifier, and a big capacitor.
Right.
But most modern supplies are switchers now that switch at some frequency from 20 kilohertz up. Now there are even high-powered supplies switching at several megahertz. So they have to be carefully shielded, and the current paths have to be carefully controlled, because in a power supply, you're dealing with currents that are quite high, and they'll create very strong magnetic fields, and at higher frequencies, combination of electric and magnetic fields called RF radiation, basically. So they have to be designed very carefully by the people who design the supply, and you'll see that semiconductor manufacturers like Texas Instruments, there'll be tutorials on how to keep the circulating current path very, very tiny on a circuit board. Mm-hmm. Because if it spreads out, then it starts radiating these fields external to the supply. And it can even back up into the power line and be carried from one device to another through the AC power. But there are regulations now, so there are filters in and out to stop a good deal of that. But even in old-fashioned power supplies, the brute force power supply where it's a bunch of diodes and some huge capacitors, the peak charging current in some of these capacitors can hit hundreds of amperes. And push hundreds of amperes through even a half-inch long piece of copper, there's significant voltage drop. So now it makes a very big difference which end of that trace or wire is tied to the chassis and which end goes to the signal circuit board.
Yeah.
Because you can easily have a shared conductor that only shares half an inch of conductor, but it's a big deal because all it takes is a few hundred microvolts in a ground system inside a piece of gear to make it noisy.
Yeah, and sometimes the thing we're spending money on is the thing that's causing us problems, and we don't want to blame the thing that we've spent the money on. So it's like you have like a denial system of it can't be the thing. No, it's not. It's not that.
I paid a lot of money for it.
I paid a lot of money for that, so it could be. Yeah. Well, speaking of paying a lot of money, like the future of audio is digital, and the future of audio still has like multiple systems connecting to things. Now that we have digital audio and we have fiber optics connecting, front of house to monitor world, and we have fiber optics connecting lighting to, the systems, et cetera. And we're moving, more digital audio, but there's still, the classic microphone on stage, the microphone preamp, all these classic building blocks of audio. In 2021, Bill, I want to be mindful of your time here. I thank you for your time. Closing up here, what are the new noises of 2021? What's hip and noise in 2021, Bill? And what are some of the things that you're seeing, maybe trends of the industry as we enter this like fully immersed digital world? Where does the humble transformer play a role in 2021, and what should we look out for? What should we all look out for here, Bill?
Well, there's two things I can say about that. Analog signal interfaces are definitely on the decline. There are fewer and fewer of those, and those are applications for classic audio transformers like the kind that Jensen makes, where you have to be very careful of what these transformers do to the signal fidelity. When you break a ground loop, that'll get rid of a noise issue, but if you choose the wrong transformer, you can end up trading that for fidelity issues. So you have to be careful and choose a good transformer. But in digital interfaces, there are still transformers there. They just look very different. They're very tiny, for one thing. Interfaces like Ethernet are extremely robust because they use transformers at both ends. So there's almost never a ground loop issue with Ethernet. On the other hand, there are digital interfaces like RS-232. I always kind of joke about RS-232 interfaces are the digital equivalent of the RCA audio connector. They are just as vulnerable to noise as RCA is to audio. So, opto isolators and things like that are often the rescue for phantom, mysterious behavior in an RS-232 interface. Anytime somebody tells me that, well, every time somebody flips a light switch in the next room, this controller over here goes crazy, probably a ground loop. And there's an RS-232 interface, so there's a little blast of extra bits going across that interface due to the noise. But there are certain parts of a system that are probably going to stubbornly hang on to being analog. One would be a microphone. I still don't see very many all digital microphones around. I think they're just not quite there yet. And at the other end, more and more power amplifiers now are turning digital, so you can get all the way from the analog at the microphone and go through an entire system and stay in the digital domain. So transformers are still going to be around, but they're going to look a lot different. Data transformers can be the size of a postage stamp and almost invisible on a circuit board because they look almost like ICs.
That's a very good point. Ethernet, it has 4 transformers on every pair, every transformer. There's a little tiny, you're right. There's transformers everywhere. So,
and the center taps on those transformers is what really enables power over Ethernet.
That's right. And a pair, and there's a negotiation there.
And pull power in opposite directions through that transformer, and get a lot of power without upsetting the transformer.
The magic of transformers, folks. Bill, thank you so very much for taking the time, joining the Toronto Audio Engineering Society. We're always privileged to have you as a part of our presentation.
Well, I appreciate being here. Canada's always been a fun place for me. I want to get back to Toronto someday.
Well, we'll have you for sure, and maybe we'll have like a face-to-face SC 0212, the connector group and the subcommittees at the AES.
Oh, yeah.
We'll get back to that. I really do think so.
All right,
sir. I'm gonna stop here. Cheers. Thank you.
All right, thank you. Have a good night.
For more information on the Toronto Audio Engineering Society, go to torontoaes.org. There you will find notifications on our upcoming events, past events, Masters of Audio, and our member showcase. The Toronto AES is brought to you by Solotech, Gear Audio, Sonotechnique, Bell Media, YSL Pro, Electrosonics Canada, BRTB, Global USS, Adamson, Lawo, avshop.ca, Q5X, and the executive team of the Toronto Audio Engineering Society.